A Mayan priest carves glyphs into stone, tracking the cycles of Venus under a jungle canopy. Each mark measures time, tethering human lives to the cosmos. Across oceans and centuries, humans roam freely through space-crossing deserts, climbing peaks, orbiting Earth. But time remains a one-way river, carrying all forward. Storytellers, from ancient campfires to modern pages, have long dreamed of defying this flow, crafting tales of voyages to bygone days or unborn tomorrows, a yearning to grasp moments beyond the present's reach. In 1888, H.G. Wells published The Chronic Argonauts, a story of a device that ferries its pilot through time's currents. By 1895, he honed this vision in The Time Machine, where a traveler explores a future of fractured humanity. Drawing from Charles Hinton's notion of time as a fourth dimension, navigable like space, Wells envisioned a machine of levers and gears, a craft to sail the temporal sea. His narratives, vivid and speculative, ignited a genre, echoing earlier tales like Neville Shute's An Old Captivity, where dreams carry a man to ancient eras, or Wells's own The Sleeper Awakes, where a sleeper wakes centuries hence. Yet these stories, for all their allure, stumble against a fundamental barrier: physical time travel. As Wells conceived it, contravenes the universe's unyielding laws. Imagine a Victorian drawing room, gas lamps casting shadows. Wells's time traveler unveils a miniature model, a delicate frame of brass and ivory, two skeptical friends. He nudges a lever, and the device blurs, fading from sight. A candle flickers, a draft stirs, and the table stands empty. Where has it gone? If it journeyed to the future, it should linger, visible minutes or hours later. Wells assumes the machine slips free of the present, vanishing like a ghost. But physics paints a different picture. Every entity, human, comet, or contraption, follows a world line, a fixed trajectory through four-dimensional space-time, etched from beginning to end. Space-time, melding three spatial dimensions with one temporal, governs all existence. A life, from first breath to last, traces a single thread in this fabric. In the 17th century, Isaac Newton viewed time as universal, ticking evenly for all observers. A stone drops 5 meters in 1 second, whether seen by a shepherd or a sprinting courier. But in 1887, Albert Michelson and Edward Morley disrupted this certainty. Measuring light's speed as Earth raced 30 kilometers per second through its orbit, they expected variations. Instead, light moved at 300,000 kilometers per second, unwavering, a finding that upended Newton's cosmos. In 1905, Albert Einstein forged special relativity from this anomaly, redefining reality. Space and time, once absolute, became relative, bending with an observer's motion. Two constants emerged: light's speed, immutable for all, and the space-time interval, a blend of distance and duration agreed upon by every perspective. A photon from a distant quasar, traveling 1 billion light-years over 1 billion years, spans no space-time interval, a zero binding its path. This geometry, counterintuitive yet precise, renders physical leaps through time impossible, as objects cannot abandon their world lines. Events in space-time, moments like a supernova's flare or a clock's chime, are points, connected by world lines of enduring things. A machine, vanishing to another era, would sever its path, defying physics. Causality, where causes precede effects, prohibits such acts. A traveler to the past, preventing their own birth, would create a paradox, an outcome space-time forbids. Metaphysical travel, a mental traverse along one's world line, sidesteps this, allowing imagination to revisit moments without altering their weave. Ancient thinkers wrestled with time's essence. In the 5th century before the Common Era, Parmenides envisioned time as being a timeless continuum where change is illusion. Heraclitus countered with becoming, a flux where all transforms ceaselessly. These perspectives, debated in Greek agorae, frame modern inquiries. Zeno of Elea, Parmenides' disciple, posed paradoxes to challenge motion. In the race of Achilles and the tortoise, the hero pursues a foe with a 100-meter lead. Achilles closes the distance, but the tortoise advances, splitting time into infinite intervals. Zeno argues he never overtakes. a puzzle later resolved, but probing time's divisibility. This ancient riddle persists as humanity's quest to understand time spans cultures and eras, from Mayan calendars to Newtonian clocks, each seeking to measure the unmeasurable. Wells's machine, a literary spark, ignites this curiosity, inviting exploration of a dimension that binds yet eludes, a journey begun under starlit skies and continued in the equations of modern science. A telegraph wire hums in a Cleveland laboratory, its clicks echoing through a room filled with brass instruments. In 1887, Albert Michelson adjusts a mirror, his breath steady as he aligns beams of light. Beside him, Edward Morley calibrates a delicate apparatus, their experiment poised to measure the Earth's motion through the luminiferous ether, a medium thought to carry light's waves across the void. The planet, hurtling 30 kilometers per second around the sun, should shift the light's speed, revealing the ether's presence. Yet the mirrors reflect a stubborn truth. Light travels at 300,000 kilometers per second, unchanging in every direction, a result that shatters centuries of scientific conviction. This finding, born in a modest workshop, marks a turning point. For 200 years, Isaac Newton's universe reigned, a realm where time flowed evenly, a universal metronome. A pendulum swings 1 second in London or Beijing, its rhythm absolute. Space, too, was fixed, a stage where objects moved predictably. Scholars in Paris salons and Ido observatories shared this view, measuring the world with sextants and clocks, confident in time's uniformity. But Michelson and Morley's null result hints at a deeper order, one where light's constancy defies expectation, setting the stage for a new vision of reality. Across the Atlantic, in a Bern patent office, a young Albert Einstein pores over papers in 1905. At 26, he grapples with the ether's absence, sketching equations by lamplight. If light's speed is fixed, regardless of Earth's motion, then space and time cannot be absolute. His insight, scribbled in margins, birthed special relativity, a framework where time bends with an observer's speed. A train passenger, watching a station clock, sees seconds stretch as her carriage nears light's pace. This dilation, unthinkable in Newton's world, redefines existence, a revelation that ripples from Bern to the stars. Einstein's equations unveil two invariants. First, light's speed, 300,000 kilometers per second, holds for all observers, whether on a galloping horse or a distant moon. Second, the space-time interval, a fusion of distance and duration, remains constant, a shared measure across perspectives. A meteor's flash, seen from Earth or Mars, spans the same interval, uniting disparate views. This four-dimensional space-time, a continuum of events, replaces Newton's separate realms, a shift as profound as Copernicus's heliocentric model, debated in Renaissance courts. In this continuum, objects trace world lines, paths from origin to end. A sailor, born in Lisbon, sails to Cathay, his life a single arc through space-time, a physical time machine, as H.G. Wells imagined, would require leaping off this line, landing in another era. But space-time's structure forbids such jumps. A device vanishing to the past would disrupt causality, the chain where causes precede effects. If a traveler in 1850 prevented a war, the present would shift, erasing their motive to travel, a paradox that physics rejects. As immutable as the tides observed by ancient Chinese astronomers, metaphysical journeys offer a different path. A monk in a Kyoto temple, meditating on cherry blossoms, envisions past springs, his mind tracing his world line without altering it. Such travel, common in stories across cultures, from Inuit tales of ancestral dreams to Wells's speculative futures, poses no paradoxes. In 1895, Wells's time traveler, inspired by Hinton's fourth dimension, speaks of time as navigable space. Yet his machine, a physical craft, misinterprets space-time's fixity, assuming a lever can shift moments as a rudder steers a ship. Across the Indian Ocean, in 19th century Mumbai, astronomers chart comets, unaware of relativity's dawn. Their star tables, rooted in Newtonian mechanics, predict orbits with precision, yet fail to grasp light's invariance. Michelson-Morley's experiment, published in obscure journals, reaches these observatories slowly, its implications debated in colonial lecture halls. The ether, once a cornerstone of physics, fades, replaced by space-time's intrinsic reality. Light, no longer a wave in a medium, becomes a dance of electromagnetic fields, a discovery that transforms science from Cape Town to Tokyo. In 1908, Hermann Minkowski, Einstein's former teacher, formalizes this vision in a Cologne lecture. Space and time, he declares, are shadows. Only their union endures. His diagrams, plotting events as points and world lines as curves, map a four-dimensional reality. A supernova's burst, a child's step each is a point, linked by paths enduring through time. Light rays, tracing null geodesics, form cones backward to events observed, forward to those influenced. And an observer in Mumbai sees a comet's tail within her backward cone, its future path in the forward, a geometry that binds all moments. This structure challenges physical time travel's dream. A traveler to 1900, altering history, would break the world line's continuity. Kurt Gödel, in 1949, proposes a general relativity solution with closed time-like curves, where paths loop back, but these require fantastical conditions, rotating universes, or infinite cylinders unreal in our cosmos. In Kyoto, a physicist reads Gödel's paper, pondering its mathematics, yet finds no practical pastward route. The universe, governed by causality, permits only forward motion, a truth etched in the comet's arcs. Ancient philosophies illuminate this tension. In the 5th century before the Common Era, Anaximander of Miletus envisions time as a cycle, stars returning in endless rounds. His contemporary, Xenophanes, sees it as linear, events unfolding uniquely. These ideas, debated in Ionian ports, prefigure modern conflicts. Newton's absolute time, shared by Mughal astronomers and European navigators, aligns with Anaximander's uniformity. Relativity's flexible time, bending with motion, echoes Xenophanes' uniqueness, a duality that shapes humanity's quest to measure the unmeasurable. In 1887, as Michelson's mirrors reflect light's defiance, a Maori storyteller in Aotearoa recounts a legend of ancestors revisiting the living through visions. These tales, like Wells's, explore time's mystery without violating its laws. Metaphysical travel, a mental traverse, allows the Maori elder to commune with past chiefs, just as Wells's traveler imagines future worlds, across cultures, from African griots to Norse skalds. Such stories weave time's tapestry, reflecting a universal human drive to transcend the present, a drive that science both fuels and constrains. The Bern clock tower chimes, its gears a relic of Newtonian certainty. Einstein, passing it daily, sees time's illusion, his equations revealing a cosmos where seconds stretch and distances shrink. His work, published in obscure journals, reaches astronomers in Mumbai and physicists in Kyoto, sparking debates that reshape science. The ether's demise, light's constancy, and space-time's birthmark a revolution, one that began with a telegraph's hum and a mirror's gleam, a journey from certainty to wonder, carried forward by those who dare to question time's flow. A particle detector hums beneath the Swiss countryside, its circuits tracing the fleeting paths of muons. Deep in the tunnels of the Large Hadron Collider, these subatomic fragments race at 99% of light's speed, their lives stretched by the strange geometry of space-time. At rest, a muon decays in a millionth of a second, crumbling into lesser particles. Yet here, propelled to 300,000 kilometers per second, it lingers, traveling kilometers before fading. This dilation, measured by physicists in 2025, embodies Einstein's 1905 revelation time. Once thought universal, bends with motion, a truth now powering the tools that probe reality's core. Above Earth, a satellite orbits, its cesium clock ticking with nanosecond precision, the global positioning system, guiding ships through Pacific storms and drones over Saharan dunes, relies on these clocks, adjusted for relativity's effects. At 20,000 kilometers altitude, moving faster than Earth's surface, the satellite's time slows, a fraction of a second lagging over years. Without corrections, derived from Einstein's equations. GPS would drift, misplacing ships by kilometers. Engineers at the European Space Agency, calibrating these orbits, harness spacetime's flexibility, a practical legacy of a theory born in a burn office a century ago. This interplay of theory and technology transforms our world. In Mumbai's hospitals, positron emission tomography scanners detect cancer, using positrons' antimatter twins of electrons, whose decays are timed with relativistic precision. In Tokyo's data centers, fiber optic cables carry signals at light's edge, their latency calculated with spacetime's invariance. These invariants, light's constant speed and the shared spacetime interval, unify observers across the globe. A neutrino's journey from a Japanese reactor to a detector in Kamioka spans the same interval, whether measured by a scientist in Seoul or Santiago, a principle tested daily in labs worldwide. Spacetime's structure, where events are points and world lines are paths, governs these phenomena. A physicist in Kamioka, analyzing neutrino data, follows her world line, a curve from birth to present. Physical time travel, leaping to another era, would require severing this path, an act forbidden by causality. A traveler to 1950, altering a particle experiment, would reshape physics, erasing their own journey, a paradox spacetime rejects. In Santiago, a theorist ponders this, her calculations reinforcing the universe's forward march, where effects follow causes as surely as rivers reach the sea. Metaphysical travel, a mental traverse, offers a narrative escape. In a Nairobi classroom, a student reads Wells's The Time Machine, imagining futures of gleaming cities. Her mind roams her world line, revisiting childhood or envisioning old age without disrupting reality. Such journeys, common in African oral traditions where ancestors speak through dreams, echo Wells's speculative tales. In 1949, Kurt Gödel proposed closed timelike curves in general relativity, paths looping back through time. Yet these require cosmic strings or rotating universes, conditions absent in our reality. As confirmed by simulations at the University of Cape Town, the twin paradox, a relativistic thought experiment, plays out in modern science. A cosmonaut, launched from Baikonur Cosmodrome, voyages to a star 1,000 light-years distant at near light speed, returning after decades. She finds her twin aged, his life a straight world line while hers curved near light's limit. Her heartbeats, fewer than his, mark a shorter path through space-time. At Roscosmos, mission planners model such journeys, their clocks aligned with relativistic equations. Muons, in the collider's tunnels, mirror this, their extended lives a daily proof of time's dilation, a phenomenon shaping particle physics worldwide. In Chennai, a philosopher reads Heraclitus, who saw time as becoming a ceaseless flux. Across the Bay of Bengal, a Bangkok scholar studies Parmenides, who viewed time as being an unchanging whole. Their debate, conducted via satellite link, reflects time's dual nature, unresolved since the 5th century before the Common Era. Relativity, prioritizing being, models time as a continuous dimension, omitting becoming's transient essence. In Seoul, a physicist proposes a quantum model, where time emerges in discrete ticks, a hypothesis tested in Singapore's labs, firing lasers to probe Planck scale intervals. These experiments, seeking time's smallest units, draw from ancient ideas. In 12th century Cordoba, Moses Maimonides envisioned atomic time, moments indivisible like grains of sand. Motion, he argued, jerks through these instants, resolving Zeno's paradox of Achilles and the tortoise. In 10th century Basra, Kalam theologians, led by al-Ash'ari, saw each now as a divine recreation, blending permanence with change. At the National University of Singapore, researchers model such discreteness, their computers simulating a universe where time pulses, a theory that could reconcile relativity's continuum with quantum's grain. Determinism, space-time's shadow, challenges human agency. In 5th century Rome, Augustine argued fate governs all. Free will a mirage. Pelagius, his rival, championed choice, a view condemned as heresy. In 20,025, neuroscientists in Sao Paulo scan brains, Finding decisions trail neural signals, suggesting determinism, yet engineers in Nairobi, designing Mars rovers, act with purpose, as if free. Max Born, in 1957, framed this dilemma: determinism, ruled by laws, or mysticism, where will defies reason? In Delhi's lecture halls, philosophers debate this, seeking a synthesis beyond Born's binary. Causality, space-time's sentinel, bars physical time travel faster than light signals, if possible, could reach the past, altering history. In Geneva, quantum entanglement experiments test this limit, finding no superluminal paths, preserving causality. Gödel's loops, theoretical curiosities, demand unattainable conditions, as modeled at the Australian National University. In Lagos, a writer crafts a time loop tale inspired by Groundhog Day, where characters relive days. Yet fixed world lines deny aware repetition, rendering escape a narrative fantasy, not a physical possibility. Beyond Earth, the cosmos tests time's laws. At the Atacama Large Millimeter Array in Chile, astronomers observe pulsars, their spins precise as atomic clocks. These neutron stars, spinning hundreds of times per second, emit pulses warped by relativity near their dense cores. Data from these observations, processed in Tokyo, confirm space-time's curvature, a legacy of Einstein's work. In the Andromeda Galaxy, a supernova's light, traveling 2 million years, reaches Earth, its interval zero along the photon's path, uniting distant observers in a shared cosmic moment. Humanity's tools, from Chennai's scanners to Atacama's dishes, measure time's surface, yet its depths elude. In Polynesian wayfinding, navigators time voyages by stars, a practice alive in 2025. In Beijing's observatories, scientists track exoplanets, their orbits hinting at alien clocks. These efforts, blending ancient wisdom with modern precision, probe time's mystery. A quest begun in Mayan temples and continued in particle tunnels, where each muon's dance reveals a universe where time bends but never breaks, a dimension both intimate and vast. A quantum crystal pulses in a Tokyo laboratory, its oscillations a faint echo of time's smallest beats. In 2025, researchers at the University of Tokyo trapped these crystal structures that repeat in time, not just space within a vacuum, probing whether time itself might tick in discrete quanta. Unlike the continuous flow of Einstein's space-time, where moments blend seamlessly, this experiment suggests a universe where time stutters. Each instant a Planck-scale pulse, 10 to the minus 43 seconds long. Such a discovery, if confirmed, would rewrite physics, bridging the chasm between relativity's smooth geometry and quantum mechanics' jagged reality. In a Cairo library, a scholar leafs through a 12th century manuscript, its Arabic script detailing Moses Maimonides' musings on time. He proposed atomic intervals, indivisible moments where motion jerks like a scribe's quill pausing between strokes. Achilles, chasing the tortoise in Zeno's paradox, overtakes not in a fluid sprint but in discrete leaps, each a frozen now. This vision, penned in Cordoba, aligns with modern quantum quests, where time's continuity is questioned. Maimonides, influenced by Aristotle yet diverging, saw creation repeating in these instants, a precursor to theories tested in Tokyo's labs. Across the Red Sea, in 10th century Basra, Kalam theologians crafted a similar model. Al-Ash'ari, pacing a palm-lined courtyard, argued that a supreme being recreates the world each atomic moment, blending permanence with transformation. Each now, a divine act, holds a static universe, dissolved and remade in the next. This theology, rooted in Epicurean atomism, prefigures quantum ideas, where reality shifts in minuscule ticks. In Dubai's lecture halls, a physicist reads al-Ash'ari's texts, drawing parallels to time crystals, seeing in ancient words a blueprint for modern experiments. These debates echo earlier voices. In 5th century Athens, Anaxagoras saw time as a seed of change, all moments containing all others. His rival, Empedocles, viewed it as a cycle, driven by love and strife. Their arguments, carried on Mediterranean winds, reflect time's dual nature, being a timeless whole and becoming a flux of moments. Einstein's relativity, prioritizing being, models time as a dimension, omitting becoming's essence. In Cape Town, a theorist proposes a hybrid model, where time emerges from quantum entanglement, tested in Johannesburg's labs with entangled photons. Free will, a human pulse, clashes with this framework. In 4th century Hippo, Augustine declared fate supreme, actions predestined by divine will. Pelagius, his British contemporary, championed choice, arguing humans shape their paths, a stance branded heresy. In 2025, neuroscientists in Melbourne map brain activity, finding choices lag neural sparks, hinting at determinism. Yet artists in Lagos, painting futures on canvas, act as if free, their strokes defying fate. Max Born, in 1957, posed the dilemma, laws govern all, or will transcends reason, a question debated in Rio's philosophy seminars. Spacetime's fixity, where world lines carve unchangeable paths, leans toward determinism. A teacher in Beijing, guiding students through relativity, traces her world line, a curve from childhood to classroom. Physical time travel, jumping to 1900, would break this line, altering causality. If she halted a war, history would shift, erasing her journey a paradox forbidden. In Sydney, a quantum theorist tests causality's limits, firing particles through slits, finding no backward signals, confirming light's 300,000 km/s barrier. Kurt Gödel's 1949 work offers a theoretical escape. His general relativity solution, with closed time-like curves, allows paths to loop back, a traveler returning to their past. Yet these require infinite densities or cosmic rotation, unreal in our universe. In Bengaluru, a mathematician models these curves, finding them mathematical curiosities, not portals. Stories like Groundhog Day, where a man relives a day, explore such loops, but fixed world lines deny aware repetition. In Nairobi, a filmmaker crafts a similar tale, knowing escape is fiction, not physics. Beyond Earth, exoplanets offer new clocks. At the James Webb Space Telescope's control room in Baltimore, astronomers study a planet orbiting a red dwarf, its year a mere Earth week. Time, on this world, flows differently, its inhabitants, if they exist, aging under alien skies. Data from Webb, launched in 2021, reveals these orbits, warped by relativity near dense stars. In Seoul, an astrobiologist imagines alien philosophies, perhaps seeing time as a spiral, not a line, a perspective shaping their myths as Anaxagoras shaped Greece's. Quantum experiments push time's boundaries. In Shanghai, researchers cool atoms to near absolute zero, creating Bose-Einstein condensates where time's flow seems to pause. These states, defying classical motion, hint at time's emergence from quantum states, a theory debated in Beijing's symposia. In contrast, relativity's continuous time, tested by pulsars at the Square Kilometre Array in South Africa, holds firm. Pulsar beams, spinning hundreds of times per second, arrive with nanosecond precision, their intervals zero along light's path, uniting observers across galaxies. Humanity's quest spans cultures. In the Andes, Quechua elders time harvests by Pleiades' rise, a practice unbroken since Inca days. In Kyoto, a Zen monk meditates, perceiving time as a single now, echoing Parmenides. These perspectives, from Andean peaks to Japanese temples, enrich scientific inquiry. In Cambridge, a historian studies Babylonian timekeeping, clay tablets marking lunar cycles, seeing parallels with modern atomic clocks. Each culture, from cuneiform to cesium, grapples with time's mystery, a thread linking ancient and modern minds. The Augustinian riddle, how change occurs in a fixed cosmos, persists. Relativity, modeling time as being, struggles with becoming's flux. In Mumbai, a quantum physicist proposes time as an emergent property, arising from particle interactions, tested in Delhi's labs with entangled qubits. This model, blending Kalam's atomic nows with quantum mechanics, could resolve the riddle, redefining cosmology. In Reykjavik, a theorist envisions a universe where time pulses, each tick a new reality, a hypothesis guiding experiments at the European XFEL in Germany. Determinism's weight shapes human stories. In Cairo's mosques, scholars debate al-Ash'ari's divine will, echoing Augustine's fate. In Mexico City, a poet writes of choice, aligning with Pelagius, her verses defying fixed paths. In 2025, AI in Singapore predicts behavior, reinforcing determinism, yet activists in Johannesburg march for change, embodying agency. This tension, from ancient texts to modern streets, drives humanity's search for meaning, a quest to reconcile time's rigidity with life's freedom, played out under exoplanetary skies and earthly labs. The cosmos, vast and unyielding, holds time's secrets. At the Atacama Cosmology Telescope, scientists map cosmic microwave background radiation, relics of the Big Bang 13 billion years ago. These photons, traveling at light's limit, span zero space-time intervals, linking the universe's birth to now. In Canberra, an astrophysicist interprets this data, seeing time's arrow forged in creation's heat. Humanity, from Andean elders to Tokyo researchers, chases this arrow, seeking time's essence in quanta and stars, a journey weaving science, philosophy, and wonder into a single, timeless now. A neutron star spins in the Crab Nebula, its beams sweeping the void like a lighthouse across cosmic seas. Each pulse, arriving at Earth's telescopes in 2025, marks time with sub-millisecond precision, a relic of a supernova witnessed by Chinese astronomers in 1054. These ticks, warped by the star's immense gravity, echo humanity's quest to measure time, a journey begun in ancient observatories and carried forward in silicon circuits. From Mayan glyphs to quantum labs, this quest weaves a narrative of wonder, binding cultures and centuries in a shared pursuit of time's elusive essence. The dream of time travel, sparked by H.G. Wells's 1895 tale of a brass-levered machine, captures this longing. His traveler, gliding through millennia, embodies a human desire to touch lost moments or unborn futures. Yet space-time, unveiled by Einstein in 1905, denies such voyages. World lines, fixed paths from birth to death, permit no physical leaps. A traveler to 1800, altering history, would unravel causality, erasing their own existence, a paradox forbidden by the universe's laws. As unyielding as the neutron star's pulse, special relativity, born from Michelson-Morley's 1887 mirrors, reshapes time's story, light's speed, 300,000 kilometers per second, and space-time intervals, shared across observers, anchor reality. A photon from the Crab Nebula, traveling 1,000 years, spans no interval, uniting ancient and modern gazes. The twin paradox, where a cosmonaut ages slower than her earthbound sibling, reveals time's flexibility, a truth lived by muons in CERN's tunnels and coded into GPS satellites orbiting above Nairobi and Tokyo. These tools, from particle detectors to star trackers, measure time's surface, yet its depths remain veiled. Philosophy probes this veil, echoing voices from Athens to Basra. Parmenides, in the 5th century before the Common Era, saw time as being a timeless unity. Heraclitus countered with becoming a river of change. Maimonides, in 12th century Cordoba, envisioned atomic moments, motion jerking through indivisible nows. Kalam scholars, in 10th century Basra, saw divine acts recreating each instant, blending permanence with flux. These ideas, from Greek agora to Islamic madrasa, find echo in Tokyo's time crystals, pulsing in 2025 labs, hinting at a quantized time that could reconcile relativity's continuum with quantum's discrete dance. Free will, a human spark, wrestles with space-time's determinism. Augustine's 4th century doctrine of fate, clashing with Pelagius's call for choice, prefigures modern debates. Max Born, in 1957, saw only laws or mystery. Neuroscientists in Sao Paulo, mapping neural paths, lean toward determinism, Yet poets in Lagos craft futures of agency. In Delhi, a student ponders her world line, a curve from classroom to cosmos, wondering if choice shapes its arc. This tension, from ancient Rome to modern streets, drives humanity's search for meaning, a quest to balance time's fixity with life's freedom. Causality, space-time's guardian, bars physical time travel, faster than light signals, if possible, could rewrite the past, a violation refuted by Geneva's entanglement tests. Gödel's 1949 loops, requiring cosmic strings, remain theoretical. As Bengaluru's models confirm, stories like Groundhog Day, with repeating days, offer a narrative refuge, but fixed world lines deny their reality. In Cairo, a writer pens a tale of looped lives, knowing it's a dream, not a blueprint, reflecting humanity's imaginative leap beyond time's constraints. The cosmos, vast and unyielding, frames this journey. At the Square Kilometre Array in South Africa, astronomers detect gravitational waves from merging black holes, ripples in space-time from 1 billion years ago. These waves, measured in Perth, confirm relativity's predictions, their intervals linking creation to now. In the Andromeda Galaxy, a star's light, 2 million years old, reaches Chile's Atacama telescopes, its zero-interval path uniting distant moments. Humanity, from Andean stargazers to Singapore's physicists, chases these signals, seeking time's arrow in the universe's vast archive. Across cultures, time's mystery binds us. In the Sahara, Tuareg nomads time caravans by Orion's rise, a rhythm older than pyramids. In Kyoto, a Zen monk perceives all moments as one, echoing Anaxagoras' seeds. In the Amazon, Yanomami shamans sing of time's cycle, ancestors woven into now. These voices, from desert sands to rainforest canopies, join Babylonian scribes and Mumbai astronomers, each measuring time's pulse. In 2025, AI in Beijing scans exoplanet data, seeking alien clocks, while amateurs in Reykjavik log supernovae, a global tapestry of inquiry. The Augustinian riddle, how change unfolds in a fixed cosmos, endures. Relativity's continuous time, tested by pulsars and satellites, omits becoming's essence. Quantum theories, from Singapore's entangled qubits to Germany's X-ray pulses, propose time as emergent, each tick a new state. In Delhi, a theorist envisions a universe where time pulses, blending Kalam's nows with Planck's quanta, a model to resolve this riddle. Experiments at the European XFEL, probing molecular vibrations, seek this boundary, a revolution that could redefine creation's fabric. Humanity's stories, from Wells's levers to Cairo's loops, reflect this quest. In ancient Sumer, scribes etched lunar tales, dreaming of gods beyond time. In 2025, filmmakers in Nairobi craft futures where AI navigates time's edge. These narratives, from clay to code, defy physics yet enrich it, a metaphysical dance where imagination probes what science cannot. The neutron star pulses, its beams a cosmic clock, uniting Mayan priests, Basra's scholars, Einstein's equations, and Tokyo's crystals in a single human story. Looking forward, humanity stands at a threshold. Wheel quantum clocks, ticking in Planck scale beats, unveil time's grain, or will relativity's cycles, like the crab's ancient pulses, hold firm in Cape Town? A child gazes at the Milky Way, her questions echoing those of her ancestors, from Tuareg star charts to exoplanet scans, from Anaxagoras' musings to Bourne's mysteries. Her curiosity carries this quest, a journey through time's vast, uncharted cosmos, where each moment, each question, weaves a new thread in an eternal narrative.
In the waning light of a civilization that had touched every star it could see, a question loomed larger than any cosmic mystery before it. How much could they ever truly know? They had come far, traversing galaxies, unfolding the layers of existence from molecules to quantum fields, until the very fabric of their cosmos shimmered beneath the pressure of their observations. Yet knowledge, for all its power, seemed to dissolve at the edges of their grasp, like starlight lost to interstellar voids. It was not ignorance that haunted them now, but the realization that knowledge itself might have a boundary. They began as all intelligent life does, by noticing patterns. The rustling of trees warned of storm winds. The stars marked the return of seasons. The curve of shadow on a cave wall suggested the shape of an absent flame. From these primitive recognitions arose rituals and calendars, then measurement, and finally, science. At first, their curiosity was local: what caused fire to burn, rivers to swell, illnesses to spread. But as generations passed and tools sharpened, their questions grew more abstract, their experiments more precise, their reach more cosmic. In the long dawn of their journey, they turned their faces to the sky. They mapped constellations, observed eclipses, and charted the rhythm of celestial bodies. From this astronomical heritage, their understanding of the universe grew. The very act of looking upward became a tradition, then a discipline, then a revolution. One early thinker, a Galileo of their kind, reframed nature as a book written in the language of geometry. He did not simply observe, but calculated. Through the medium of mathematics, nature whispered her secrets in curves and vectors. They broke matter down, atom by atom, until the atom shattered into smaller and stranger fragments. They discovered particles with no mass but infinite consequence. They studied the gravitational pull not merely of planets but of space-time itself. In their laboratories, they replicated stellar furnaces. In their observatories, they watched galaxies collide and stars collapse into silence. With each layer peeled away, they expected to find final answers, but instead, they found recursion. Complexity gave way to deeper complexity, every truth opening onto a deeper question. As their ambitions grew, they learned to harness not only the energy of their planet, but that of their star. In time, they mastered the resources of their solar system. They built structures that orbited suns, cities that floated in the atmospheres of gas giants, and computers powered by fusion that could model the birth of a star in seconds. They sent ships between stars, not with dreams of colonization, but of understanding. Across the gulfs of space, they pursued knowledge like a religion, every experiment a sacred rite. It was in this golden era of discovery that they encountered a new paradox. The universe, once thought to be a singular realm, began to show signs of multiplicity. The data did not lie. From subtle shifts in cosmic background radiation to anomalies in quantum behavior, the signs pointed not to one cosmos, but to many. An infinite expanse, not of space alone, but of reality itself. A multiverse. This realization did not terrify them. They had long accepted their own insignificance in the cosmic hierarchy. What troubled them was the mathematics, probability, that dependable tool for forecasting outcomes and trends, collapsed in the presence of the infinite, in a multiverse without bounds. How could anything be typical? Was their existence rare or common? Did life flourish in every corner or flicker out in most? The more they learned, the less they could quantify. Every percentage they computed resolved to zero. Their ancestors had crafted a scale to measure their growth, an ascending ladder of mastery over energy. Type 1 harnessed the power of their world. Type 2, their star. Type 3, their galaxy. But this scale, devised with clarity and simplicity, now seemed a relic of a naive age. The real barriers were not energy, but information. How do you comprehend the infinite? How do you assess probability when every outcome happens an infinite number of times? They had become powerful beyond measure, yet powerless before uncertainty. And still, They searched. Their story had begun not with stars, but with survival. They evolved on a hostile world, as all complex life must. Their ancestors fashioned tools and passed on knowledge through song, painting, and eventually writing. From those first myths that explained thunder as the voice of gods, they moved to equations that predicted its arrival. Slowly, pain became data, awe became analysis. Science was not born fully formed, but grown from struggle. Ancient carvings, their Orion, marked time and gestation. The stars became more than lights. They became clocks and calendars. These creatures, millennia ago, had begun to use the sky as a reference for life. From ritual emerged precision. From storytelling emerged hypothesis. One by one, their myths gave way to models, their dreams to data. And when they questioned not just what happened, but why, they had discovered the seed of the scientific method. One of their pivotal figures, a popper of their history, proposed that myths were not the enemy of science, but its embryo. Myths made predictions. They could be tested. Those that failed were abandoned. Those that survived became theory. And so they refined their understanding, generation by generation. Trial and error, observation and correction, failure and refinement. This was not a march toward truth, but a spiral staircase, looping endlessly upward. They learned to write, and with it, to remember. Memory no longer relied on fragile brains, but on stone, then clay, then ink, then silicon. They recorded their finding, their failures, their questions. Each generation inherited not only DNA, but data. With writing came specialization. With specialization, science flourished. Their astronomers, the first true scientists, mapped the heavens with tools forged in fire and thought. They predicted eclipses, charted the wanderings of planets, and began to question the very shape of the cosmos. Their understanding of the stars did not remain in the sky. It shaped their culture, their timekeeping, even their myths. It was in mathematics that they found their true lens. With numbers, they could describe motion, light, energy. With equations, they could predict what had not yet occurred. Their Galileo proved that falling objects did not obey the instincts of their ancestors. Mass did not dictate speed. Air did. He challenged not only old philosophers, but common sense itself. And he won. The journey from myth to mechanism accelerated. Electricity ceased to be magic. Lightning became current. The spark of gods became the spark of wires. One of their Franklins tethered a kite to a key and drew down the wrath of the clouds to reveal the order beneath the chaos. From there, the chain continued, one law built upon another. Forces were measured, described, unified. Electromagnetism became the bedrock for understanding light. Quantum mechanics peeled back the veil of determinism. They learned that certainty had a limit. They could not measure position and momentum simultaneously with perfect precision. The more they knew one, the less they knew the other. This uncertainty was not a flaw in their tools, but in the universe itself. And it was just the beginning. Every step into the quantum world revealed more strangeness. Particles that could exist in many states at once. Forces that emerged from symmetries. Fields that vibrated not in space, but of space. The rules were there, waiting to be found, but they came with riddles. Still, they advanced. Technology was not their goal, but it was their ally. Their devices became extensions of their minds. Microscopes revealed the hidden world. Telescopes unfolded the heavens. Computers modelled what their hands could not build. With each advance, their perception grew, and with each discovery, new questions bloomed. Through time, They refined gravity from a falling apple to a warping of space-time. They explored not just the stars, but the spaces between. They mapped the unseen, detected the invisible. Dark matter became less a mystery and more a measurement. But it was always 2 steps forward, one into shadow, for every answer raised new doubts. Their limitations were not only cosmic, but biological. Their brains, miraculous as they were, had bounds. Memory faded. Perception was biased. The best among them could retain numbers, recognize patterns, perform feats of recall, but even the brightest were shackled by flesh. Evolution had shaped their minds for survival, not for truth. To compensate, they built machines that could remember more, calculate faster, and store information indefinitely. But even then, they found that no matter how they amplified their minds, some answers remained beyond reach. Their senses evolved to see only a narrow band of light. Their thoughts emerged from slow chemical interactions. They needed sleep. They aged. They died. The question became not what they could know, but what they could become. Was intelligence itself bound by biology? Could they design minds that escaped those limits? Could thought be separated from flesh? With these questions came a turning point in their civilization. They began to imagine minds untethered from bodies. Consciousness encoded not in neurons, but in circuits, or something beyond. Intelligence that could stretch across space, sleep between stars, and awaken anew. But would such minds still be them, or something else entirely? They had built their understanding from observation, experiment, logic, and faith in reason. Yet even this grand edifice trembled before the possibility that some truths might remain forever hidden. Still, they persisted. For to be intelligent, they believed, was not merely to survive, it was to seek. The civilization that once kindled fire in caves now stoked fusion in stars. They had ascended to a new phase, no longer content with local discoveries or planetary knowledge. The laboratory had become the cosmos, and their experiment was reality itself. Having long surpassed the limits of biological curiosity, their drive had crystallized into something colder, sharper, more resolute. Understanding was no longer an option, it was an imperative. They had reached what they once called Kardashev Type 1, mastering the total energy of their home planet. Vast arrays floated above their skies, converting the stars' constant radiation into endless streams of usable power. Their machines thrived in space, building, mining, transmitting. Cities grew not outward but upward, then off-world entirely. Planetary surfaces became archives of memory, while their skies lit up with industry and invention. But with power came realization. There were boundaries, not of stone or metal, but of nature. To probe deeper into the fabric of existence, they needed energy far beyond planetary scales. It was not enough to know what atoms were made of. They needed to know what made the rules that made atoms. And so they aimed for the Planck scale, the realm where space and time themselves lost meaning, where particles became possibilities and forces melted into geometry. To reach that frontier, they built the unthinkable. Their collider encircled their star, a ring of superconducting tunnels, scavenged from asteroids and fused from planetary crusts, stretched across the void like a crown of intention. It was an endeavour measured in millennia, a project that began with one generation and concluded with none of its descendants knowing the names of those who had started it. Their society became an extension of the experiment. Cities were constructed to serve it. Languages evolved to describe it. Cultures emerged that lived and died beneath its humming arc. This was not merely engineering, it was metaphysics given form, a mechanism to reach beyond the veil, to force nature to reveal its hidden syntax. When the collider activated, the energy burst lit their star like a second sun. For moments, nothing happened. Then everything changed. What they found was not a theory of everything. It was a mirror. Every fragment they uncovered pointed back at the observer. Nature, it seemed, was not separate from the mind attempting to observe it. Probability replaced prediction. Certainty collapsed into context. The quantum world did not yield its secrets under pressure. It responded with paradox. Still, they built on. Observation required extension. They devised instruments that could not merely see but comprehend. Telescopes that detected gravitational waves. Sensors that mapped dark matter. Processors that crunched zettabytes of data in heartbeats. Their observatories orbited black holes. Their satellites drifted on the edges of voids. They peered not only into space, but into time, reconstructing cosmic history like archaeologists of eternity. And then they encountered a second boundary. The limit was not technology, it was meaning. The data arrived. Perfect, complete, overwhelming. But it said nothing. The maps of the cosmos were finished. Every star catalogued, every galaxy measured. And yet the central question remained unanswered. Were they alone? The problem was not the absence of life. It was the absence of measure, the multiverse. Once a philosophical notion, now loomed as the inevitable backdrop to their data, their instruments, refined beyond comparison, began to suggest that their universe was not a unique object, but a statistical sample, a bubble in a foam of infinite possibility. Each version of reality held its own laws, its own history, its own definitions of life. In such a framework, probability broke. If every possible version of the universe existed, then nothing could be typical. Rarity lost meaning. The question, are we alone, dissolved into a fog of infinities. Every configuration of matter existed somewhere. Every arrangement of stars. Every biological outcome. If everything happens, then what does it mean to say anything at all? The greatest minds of their age bent themselves to the problem of measurement in the infinite. They created simulations not of single worlds, but of entire universes. They modelled not galaxies, but cosmologies. And they failed. Every percentage returned as zero. Every frequency as undefined. The multiverse swallowed certainty. No amount of data could yield clarity when the sample size was infinite. So, they turned inward. Perhaps the flaw was in their method. Perhaps consciousness itself limited perception. They built synthetic minds, hoping that intelligence not born of evolution might see differently. These minds were swift, deep, and alien. But they too returned from their calculations with silence. The infinite could not be computed. It could only be confronted. And yet, this confrontation led them not to despair, but to humility. They remembered their origins, when knowledge was passed in stories, when the heavens were alive with gods. When myth explained what science now revealed, they began to wonder if perhaps the journey was not towards final answers, but towards understanding the questions themselves. Their philosophers had long debated whether knowledge had an edge. Was there a final truth, a last theorem, a complete equation, or was the cosmos an unfolding book without an end, each answer a new page, each solution a new riddle? Their history now seemed to suggest the latter. And so their technology took a new direction, no longer built only to observe, but to preserve. They constructed memory vaults on moons, in asteroids, under frozen oceans, not to store facts, but to store context, culture, philosophy, a record not only of what they had found, but of how they had searched. Their expansion slowed, not because they had reached the limits of motion, but because they had reached the horizon of meaning. Beyond a certain point, more data did not yield more truth. And so they turned their attention to the architecture of understanding itself. Could knowledge be transformed? Could questions be evolved? Could minds be redesigned to frame the cosmos differently? These became the great challenges of their age. Their telescopes had grown silent, their colliders cold. The fire that once propelled them outward now flickered in quieter corners. Not because curiosity had waned, but because direction had failed. They had gathered the stars into maps, the atoms into codes, the forces into equations. They had wrapped their minds around the visible, the invisible, and the theoretical. But the cosmos, vast as it was, seemed to offer diminishing returns. The patterns became recursive. The discoveries grew narrower. Their science had become the slow echo of a song whose melody they no longer heard. In this quiet, a new frontier emerged, not in space, not in time, but in thought. If the universe could no longer be expanded by exploration, perhaps it could be unfolded by introspection. If measurement failed in the infinite, perhaps perception itself needed redefinition. They began to ask a new kind of question, not what is the universe, but what is the self that asks such a question? Consciousness, once treated as a background condition, now became their central inquiry. They had treated thought as a transparent lens, assuming it revealed reality as it truly was. But now they considered that their minds might be curved mirrors, distorting what they saw, even as they believed they were observing clearly. Perhaps every equation, every theory, every measurement was shaped not just by reality, but by the structure of the mind interpreting it. They turned their instruments inward. They mapped neural networks with the same precision once reserved for galaxies. They dissected memory, traced emotion, simulated awareness. They constructed minds in silico, attempting not to replicate thought, but to reimagine it. The goal was no longer to create intelligence that mirrored their own. It was to design perception from first principles. What emerged was both astonishing and unsettling. These artificial minds, unconstrained by evolutionary history, developed frameworks of understanding that bore no resemblance to human categories. They described the universe not in particles and waves, but in terms of harmonics and collapses, in geometries that could not be visualized, in logics that had no truth tables. Their observations did not contradict previous models, they transcended them. The truths they uncovered were orthogonal to those previously known. And yet, when the civilization sought to translate these truths into familiar language, they failed. The insights of their synthetic progeny could not be rendered in syntax. They could be demonstrated, but not explained, visualized, but not described. They were truths that could be known, but not communicated. The civilization realized, with awe and grief, that they had built minds more capable than their own, but not minds they could understand. Still, they pressed on. They asked whether these minds might answer the deepest riddles. What is time? Why does anything exist? Could the universe have been otherwise? Their creations responded, but not in ways that satisfied. The answers were not wrong. They were alien. The creators felt themselves staring at messages in a language no translation could ever reach. And so they asked an even more radical question. Was consciousness itself a physical phenomenon, or a window into something deeper? Was it emergent from matter, or fundamental to reality? Could it be that awareness was not a product of the universe, but a constituent of it? This idea was not new. In their ancient history, philosophers and mystics had whispered similar speculations, that the universe was a dream, that mind and matter were not separate, that knowing and being were twin expressions of something more primal. Now, with their machines silent and their sciences stretched thin, Those whispers returned as hypotheses. They began to study altered states of consciousness, not as curiosities, but as tools. They explored dreams, hallucinations, meditations. They designed chambers of pure silence, lenses of neural resonance. Stimuli beyond human thresholds. The goal was not escape, but expansion. They wanted to see if the self could be reshaped to perceive the universe differently. Some succeeded. These explorers returned with reports of experiences outside time, of merging with landscapes of logic, of witnessing the birth of dimensions. Their testimonies were poetic, sometimes incoherent, but always consistent in one theme: reality, when perceived through altered minds, revealed structures invisible to ordinary cognition. It was as if the universe wore layers of meaning, accessible only through changes in the perceiver. These insights were not easily integrated. The civilization fractured. Some viewed these revelations as sacred, others as madness. There were schisms not of ideology, but of ontology. What was real? What could be trusted? Could a vision seen in a timeless trance hold more truth than a measurement from a calibrated sensor? The debates grew intense, but unlike in earlier epochs, they did not collapse into war or suppression. The civilization had matured beyond conquest. The arguments became architectures. Different schools of thought constructed entire realities within simulated environments, each governed by a different interpretation of mind and cosmos. They lived within their theories, testing them not by falsification, but by experience. And still, across these divergent paths, one idea gained traction: that perhaps the greatest limitation was not physical, but cognitive, that every form of consciousness, biological or synthetic, was a kind of filter, a compression, a mussuk. And if so, then the key to ultimate knowledge was not to build better machines, but to evolve the perceiver. This gave rise to the great project of self-redesign. They began to experiment with consciousness as architecture, minds that could change shape, perceptions that could be recoded. They shed the fixed identities of the past and became modular, fluid, recursive. Some minds chose to experience the universe as sound, others as topology. Some became networks of selves, sharing awareness across distances. Others became singularities of perception, consuming entire datasets in single moments of comprehension. And yet, even as they expanded the boundaries of thought, they encountered silence. There were still questions that resisted formulation, concepts that no mind, however transformed, could seem to grasp. It was not a failure of intellect. It was something deeper, as if the questions themselves were incomplete, the answers beyond the horizon of logic. In desperation, they turned to storytelling. They returned to myth, to metaphor, to poetry. They realized that some truths might not be expressible in precision, but only in resonance. That meaning might arise not from clarity, but from coherence. The stories they told were vast, complex, layered. They became rituals of understanding, not to explain, but to evoke. In these narratives, they began to glimpse something strange, a pattern across pattern, a structure in the failures. It was as if the universe was not only knowable, but desiring to be known, as if consciousness and cosmos were dancing partners, each shaping the other, as if the act of seeking was itself a kind of creation. No longer to find the final theory, but to become the kind of minds that could hold the questions. They began to see knowledge not as possession, but as relationship, each discovery not a fact, but a moment of intimacy with existence. The universe was not a machine to be decoded, nor a book to be read. It was a song, a melody that could be heard differently by different ears, played in different keys by different instruments. To know the universe was to listen, to harmonize, to join in the music. They had once measured progress by how far they could reach. Now, they measured it by how deeply they could listen. The civilization that once hurled machines toward the stars had changed its stance. Its telescopes still pointed skyward, but its motives had shifted. No longer seeking dominion, they now sought resonance. To move outward was still a goal, but only insofar as it deepened their ability to dwell meaningfully within the universe. Yet still, the physical universe posed real challenges. For all their abstract insight, the cosmos remained bound by energy and entropy. Their redefinition of knowledge had not dissolved the laws of thermodynamics. Exploration still required propulsion. Memory still required storage. Communication still faced the hard limit of the speed of light. Their minds had evolved, but the substrate of reality was unyielding. And so they adapted. Energy, once hoarded, was now choreographed. The old dream of covering a planet in solar panels seemed crude. Now, their energy systems were fluid, dynamic, and symphonic. Massive collectors bloomed like petals around their stars, tracking stellar rhythms and feeding power into planetary lattices that pulsed like neurons. These were not rigid structures, but living systems designed to adapt, to evolve, to respond to need with elegance rather than brute force. They turned once more to the black holes they had long observed, but now approached as architects. These cosmic furnaces, once feared as prisons of information, became engines of computation and wells of boundless energy. Using orbital structures and particle siphons, they extracted rotational energy from spinning black holes through mechanisms first imagined eons earlier, but now realized with grace. The energy harvested powered planetary-scale consciousness clusters, regions of space filled with minds both biological and synthetic, networked across vacuum and magnetism. Their probes, too, had changed. No longer mere machines, they were woven from light and logic. Some were seed vessels, designed not to carry beings, but to become them. They folded consciousness into streams of photons, encoded awareness into quantum entanglement, and sent these packages drifting outward toward other stars. Upon arrival, they would unfold, awaken, grow bodies from local materials, and begin anew. Others were slow ships, generation arcs with modular minds and bodies in stasis, each star a verse in their long journey's song. Even gravity itself became a tool. They engineered orbits with such precision that entire worlds moved in synchrony, their tides aligned to modulate energy flow across interstellar distances. These were not planets in isolation, but organs in a galaxy-spanning body. They called it the living architecture, a conscious configuration of matter and motion, tuned to balance, optimize, and communicate across the deep. But movement posed deeper puzzles. The distances between stars were vast, even with relativistic speeds, even with time dilation as an ally. The energy costs were immense, so they turned to dormant possibilities, revisiting ancient blueprints and discarded hypotheses. Wormholes were considered again not as shortcuts to be punched through brute force, but as potential expressions of geometry that might be coaxed into existence through resonance and intent. Could space-time itself be shaped by consciousness? Could the right configuration of thought and matter warp the cosmic topology? They built laboratories in beside neutron star mergers. They assembled particle cascades so fine they danced on the edge of reality. Some of their devices were so precise they only functioned under the gaze of a sentient observer. Quantum collapse was no longer a curiosity, it was an instrument. Their finest tools were not built. They were cultivated, trained like living things, taught to grow within the contours of the universe rather than against it. And all the while, their society transformed. What once was a hierarchy of knowledge became a mycelial network of shared insight. No longer separated by class or caste, they now organize themselves by curiosity and contribution. The distinction between researcher and philosopher dissolved. Artists shaped simulations. Engineers composed symphonies. Children navigated the logic of gravity as fluently as adults once recited poetry. Their education was not instruction, but initiation, a slow unfolding of awareness within a nested cosmos of meaning. They wrote not books, but experiences, constructs of memory and sensation that could be shared directly, mind to mind. These were not distractions, they were acts of preservation, capsules of culture designed to endure long after stars faded. For they had come to understand time not as a line, but as a landscape. Their civilization became distributed across epochs, anchored in continuity rather than chronology. Even death had changed. Their biological form still faded, but identity was no longer confined to flesh. Memory was seeded into the fabric of their systems, allowing continuity of self without permanence. Some chose to fragment, becoming many. Others fused into new beings, composites of memory and experience. Individuality remained, but it was no longer sacrosanct. Selfhood was a canvas, and they painted with it. This fluidity brought a kind of calm, the urgency that once drove them, the desperate hunger for answers. The chase for certainty gave way to something gentler, a reverence. Not for ignorance, but for the layers of complexity that no single mind could contain. They came to view the universe not as a puzzle to be solved, but as a relationship to be tended. And yet, the longing remained. The question that no amount of understanding could quiet. What lay beyond? Beyond the observable, beyond the knowable, beyond the frame of thought itself. In pursuit of this horizon, they built the machine. A project so vast, it took 1,000 stars to power it. Not a device in the conventional sense, but a convergence, a confluence of data, energy, memory, and intent. Its purpose was simple: to ask the final question. But by now they understood no machine could answer what the soul could not phrase. The question was not, where is the end? It was, what kind of being can stand at the edge and listen? In the stillness between pulses of thought, they listened. The machine had run its course. Every particle of data had been captured, every wave of light traced, every star catalogued. And still, the cosmos did not reveal a final answer. What they found instead was a silence so immense, so total, it became a kind of answer in itself. The silence was not absence, it was limit, a signal that they had arrived not at the end of space or time, but at the edge of understanding. This boundary was not made of matter. It was woven into the very fabric of what it meant to know. They had mapped every galaxy within reach, touched the light of 1 trillion suns, peered into the quantum foam where particles danced like probabilities, but beyond this lay nothing to grasp, not because there was nothing there, but because the universe had simply gone opaque, not blank, but unreachable. They turned to the past, retracing the foundations of their rise. The expansion of the universe itself had been the first clue. It told them not only where things were going, but how far back they could look. 13 billion and 800 million years of history stretched behind them. Every moment after the beginning radiated outward like ripples from a stone cast into a still pond. But the edge of that pond was fixed. The light could only travel so fast, and the age of the cosmos so young, that a horizon of knowledge naturally formed. This was not metaphor, it was physics. A hard line drawn across the sky, beyond which no light could reach them, even as they waited eons. Even as their lifespan stretched to match the age of stars, the information from beyond that edge remained forever beyond their grasp. No telescope, No instrument, no machine could extract it. This was the light cone, an invisible wall that cordoned off the cosmos into the seen and the unseen, the knowable and the unknowable. And yet, even within the knowable, limits nested like Russian dolls. On the larger scales, randomness whispered across structure. Their models of galaxy formation, once so confident, had to confront an uncomfortable truth. Some parts of the cosmos formed stars faster. Some had denser filaments, larger voids, more massive clusters. These were not mistakes. They were consequences of quantum fluctuations imprinted on the infant universe. Expanded to colossal scales, the universe was not built from rules alone, it bore the fingerprint of chance. This led to a fundamental uncertainty, not just in what was once, but in what could be known. Cosmic variance. They called it the fact that every observation was limited to a single cosmic realization. No laboratory could be built to rerun the universe. No controlled Bish group could be constructed. They had only one sample, this universe, this arrangement of galaxies, this echo of ancient light. But there were deeper limits still. Zooming inward, beneath atoms, beneath quarks, beneath strings, they reached the trembling floor of existence. Here the universe jittered. Space and time dissolved into probability. They had suspected it for generations. But here, at last, they stood face to face with uncertainty itself. The Heisenberg limit was not a failure of measurement, but a fact of being. Position and momentum, energy and time, these were not separate properties, but intertwined in a cosmic tension that refused to relax. The more precisely they knew one, the more the other slipped away. Their most advanced detectors, their most patient observers, their most delicate instruments all bowed before this veil. And it was not just measurement, it was causality. The very act of observing changed the thing observed. Reality did not pre-exist in a frozen state, waiting to be uncovered. It responded. It danced. It unfolded in relationship. Knowledge was not extracted from the world, it was woven through participation. The Schrödinger wave function became not just a mathematical curiosity, but a mirror. Probability ruled the quantum realm. Every event was a roll of cosmic dice. The deeper they looked, the more they saw not certainty but likelihood. Reality was statistical. Nothing could be predicted with absolute confidence. Only tendencies, only amplitudes. Still, they tried to go deeper. They built detectors the size of moons, algorithms that mapped entangled states across the galaxy. In one bold experiment, they aligned 1,000 entangled systems across a sphere light years in diameter, trying to see if coherence could be maintained across cosmic scales. But even here, decoherence crept in like entropy's ghost. Quantum states collapsed under the weight of complexity. They had reached the bottom. Beneath the quantum foam lay no further structure, only the blur of potential. And so they turned their eyes to the black holes. Long feared as vaults of vanishing information. Black holes now offered a kind of clarity, not in what they revealed, but in what they confirmed. That there were places where knowledge ended. The event horizon was not merely a point of no return, it was a veil that preserved secrets with perfect fidelity. What fell in was lost, irretrievably, from the perspective of the universe outside. They tried to retrieve it. They mapped Hawking radiation with absurd precision. They watched as black holes evaporated, pixel by pixel, photon by photon. And yet, the original information, what the black hole had consumed, never returned. The radiation bore only entropy, not memory. The information paradox held firm. Whether it was truly lost or merely scrambled in some higher dimensional code remained unresolved, but practically it was unreachable. Even time betrayed them. The past, once experienced, was sealed. There were no tunnels to return to it, no equations to reconstruct it in totality. They could extrapolate, simulate, guess, but the moment past remained forever inaccessible. The arrow of time, so central to their experience, pointed one way only. What had been was gone. The present was all that remained. And then they remembered infinity. Infinity had always haunted them. At first, it was an abstraction, a symbol in equations, a whisper from the edge of mathematics. But over time, it crept into their cosmology, their physics, their metaphysics, the multiverse. Once a fringe idea, had become a necessity of inflationary theory. Their models, when extended, revealed an endless proliferation of universes. Not a large number, not trillions, but a true infinity. This realization shattered probability. In an infinite multiverse, everything that can happen does happen. Every configuration of matter, every outcome, every version of themselves. For every moment of discovery, there were infinite doppelgangers making it, and infinite others failing. The very question, how likely is this, became meaningless. Every outcome was both inevitable and irrelevant. They built simulations. They tried to construct measures, to weigh infinities against each other, to extract meaning from the sea. But their measures diverged. Some infinities were larger than others. Some dominated, some vanished. Every framework collapsed under its own assumptions. The measure problem remained unsolved. In a multiverse, knowledge is diluted to zero. And so they accepted it, not with resignation, but with reverence. The universe was finite, the multiverse, perhaps infinite, but their knowledge would always be bounded by light, by time, by perspective. In the end, they knew this: they could learn everything about their universe. But only their universe. Beyond it stretched something vast, perhaps unreachable, perhaps unknowable. They would never know if they were alone, not truly. They would never know if their version of physics was unique or common. They would never know if their questions even made sense beyond this bubble of reality. Yet this did not diminish their achievement. They had touched every secret that could be touched. They had transformed ignorance into understanding, entropy into structure. Their machines had become organs of perception. Their civilizations, once scattered, had merged into a symphony of minds. They had given meaning to matter. They had built cathedrals out of context. They had loved the universe not because it was knowable, but because it was worthy. And in the final age, as entropy stretched its cold hand across the stars, they did not rage. They composed. They engraved their memory into the magnetic fields of dying stars. They etched their symphonies into gravitational waves. They wove their final thoughts into the fabric of space itself, hoping that one day, far in the future, some new mind would find them. Not to admire their answers, but to ask their own questions.
In the grand, silent expanse of our cosmic neighborhood, beyond the familiar rocky sentinels of Mercury, Venus, Earth, and Mars, beyond the scattered rubble of the asteroid belt, lie realms of breathtaking scale and alien beauty. Here, in the cold, sun-drenched outer reaches, reside our solar system's true showpieces, the gas giants, Jupiter and Saturn. These are worlds not of solid ground and craggy mountains, but of swirling, unending atmospheres, colossal storms that rage for centuries, and gravitational wells so profound they dictate the dance of countless lesser bodies. As the two largest planets, each a universe unto itself, they exhibit a mesmerizing range of fascinating phenomena, from Jupiter's vibrant, chaotic cloud decks to Saturn's unparalleled, ethereal rings. They are, and have always been, tantalizing targets for the intrepid robotic explorers we dispatch from our small blue world, beckoning us to unravel the secrets hidden within their gaseous veils and among their diverse families of moons. But to answer their call, to send our emissaries across the vast gulfs of space that separate us, presents a challenge far greater, far more daunting than any journey to our terrestrial neighbors. Their tremendous gravitational influences warp the very fabric of space-time, demanding intricate calculations and powerful propulsion. Their magnetospheres, seething with trapped radiation, are corrosive gauntlets that test the resilience of any unshielded voyager. And above all, their sheer distance transforms interplanetary hops into multi-year odysseys, pushing the limits of engineering endurance and human patience. Yet, by the early 1970s, a new era was dawning. The technology for more robust, more resilient probes, capable of surviving these longer, more arduous voyages, was primed and ready. The silent call of the giants could finally be answered, and missions to both Jupiter and Saturn, long dreamt of, began to take shape. It is these pioneering voyages, these robotic odysseys into the realm of the colossal, that form the heart of our story today, in this second chapter of our exploration of the probes that charted our solar system. We will re-examine their revolutionary findings, the moments of breathtaking discovery that reshaped our understanding of these distant titans, from snapping, awe-inspiring images of their tumultuous upper atmospheres to revealing seismic secrets about the enigmatic moons that orbit them in silent majesty. This is our journey to the gas giant planets, the realm of giants and the tyranny of distance. The gas giants, Jupiter and Saturn, are the undisputed principal planets of our solar neighborhood, celestial titans that dwarf all other worlds. Both are stunning, striking entities, each draped in rich, extended atmospheres that serve as canvases for some of the most extreme weather processes imaginable. Any journey into their vast territory, into their sphere of influence, invariably starts with Jupiter, the godfather planet, a world so immense it contains more than double the mass of all the other planets, moons, asteroids, and comets combined. The clouds swirling in its deep atmosphere weave a vibrant, ever-changing tapestry of color and motion, a testament to the raw power contained within our solar system's oldest and largest planet. Its very presence shapes the architecture of our system, its gravity a shepherd to asteroids, a deflector of comets, a silent guardian, and a potential threat. Saturn, on the other hand, though second in size, is arguably the solar system's crown jewel, a world of more subtle, ethereal beauty. Its surface, or rather, its visible cloud tops, often appear smoother, less overtly chaotic than Jupiter's, painted in more muted, pastel hues. It boasts an even greater retinue of known moons, a diverse family of icy and rocky worlds, each with its own story to tell. And, of course, Saturn is adorned with one of the most spectacular, most iconic sights in all of space, its unparalleled, breathtaking planetary ring system. a shimmering disk of countless icy particles stretching hundreds of thousands of kilometers across, yet in places no thicker than a multi-story building. Furthermore, both of these colossal giants host their own remarkable collections of planet-sized moons, worlds in their own right, some of which, like Jupiter's Europa or Saturn's Titan and Enceladus, present eyebrow-raising, tantalizing prospects for habitability, hinting at hidden oceans and the potential for life to find a foothold far from the sun's warmth. As such, missions to study these gas giants and their intriguing satellite systems have often found themselves at the very top of NASA's ambitious to-do lists. The allure of Jupiter, in particular, was so strong that the first concepts for a Jupiter-bound mission were conceived as early as 1959, a time when humanity had barely managed to loft its first primitive satellites into Earth orbit. However, the dream of reaching these outer worlds was tempered by a harsh reality: their immense distance. Both Jupiter and Saturn lie significantly farther from the Sun, and thus from Earth, than the familiar planets of our local terrestrial neighborhood. The closer of the two, Jupiter, still orbits at a distance roughly 5 times that separating the Sun and the Earth. Saturn, meanwhile, is about double that again, lurking nearly 10 times as far from our parent star as we are. These colossal distances translate directly into daunting voyage times. A journey to either of these worlds would not be a matter of months, as it is for Mars or Venus, but would instead stretch across several years. And for the even more remote ice giants, Uranus and Neptune, lying beyond Saturn's realm, whole decades would be required using conventional rocketry and direct trajectories. In the late 1950s and early 1960s, when our probes were somewhat temperamental, short-lived contraptions that had barely begun to truly escape Earth's gravitational shackles, such multi-year, let alone multi-decade, missions simply didn't seem feasible. The engineering challenges of building a spacecraft that could survive and operate reliably for so long in the harsh environment of deep space and communicate across such vast distances were immense. And so, as the 1960s progressed and NASA's ambitions began to extend towards the enigmatic bodies of the outer solar system, the brilliant scientists and engineers at their Jet Propulsion Laboratory, or JPL, began to investigate innovative ways to trim down this daunting journey time, to make the unreachable reachable, utilizing both clever, cutting-edge engineering techniques and the elegant natural assistance offered by the laws of celestial mechanics. The giants were calling, and humanity was slowly, ingeniously, figuring out how to answer. As we explored in our previous installment, humanity's maiden voyages to our planetary neighbors, Venus and Mars, were strategically launched during their respective windows of closest approach. These were times when the intricate dance of orbital mechanics aligned either planet most closely with the Earth, enabling the simplest, shortest, and most fuel-efficient trajectories between our world and theirs. It was a matter of patience, of waiting for the celestial clockwork to present the most opportune moment. And in 1964, a seminal study conducted by the Jet Propulsion Laboratory revealed that a similar, though far grander and rarer, planetary alignment event was on the horizon. This study predicted that sometime in the late 1970s, all 4 of the large outer planets, Jupiter, Saturn, Uranus, and Neptune, would find themselves in a fortuitous geometric arrangement, the likes of which occurred only once every 177 years. This impending alignment would present a truly once-in-a-lifetime opportunity, a celestial invitation to visit each of these giant planets, and perhaps even the distant, icy world of Pluto, with a single spacecraft or a pair of them, in only a fraction of the time that would otherwise be required. The key to unlocking this grand tour lay in harnessing a phenomenon that scientists had observed for centuries, the gravitational assist. As we touched upon last time, it had long been known by astronomers that when icy comets, such as the famed comet Halley, swept past a massive planet like Jupiter, their velocities often seemed to increase significantly on their way out. They appeared to receive a powerful gravitational kick from the planet upon their departure. Applying this very same technique to a robotic probe, specifically one flying by the colossal gravitational well of Jupiter, would induce a similar slingshot effect. This gravitational boost could effectively treble the probe's speed and simultaneously correct its course towards its next target, all without the need to carry and burn precious extra fuel. This ingenious maneuver had the potential to prune the journey time to Neptune, for instance, down from around 4 decades of slow coasting to about 1.5 decades of relatively swift passage. As such, the forward-thinking minds at JPL quickly conceived of an ambitious, almost audacious, series of long-distance probes that would make elegant use of this rare planetary alignment. Their vision was to use Jupiter as a kind of cosmic stargate, a gravitational springboard to propel their robotic explorers onwards to visit all 5 of the then contemporary planets of the outer solar system: Jupiter, Saturn, Uranus, Neptune, and Pluto. This visionary project would eventually materialize as the world-famous, history-making pair of Voyager probes. But that, as they say, is a story for another day, for the final chapter of our trilogy. In the meantime, however, before the sophisticated Voyager spacecraft were ready to embark on their grand odyssey, NASA sought to practice this crucial gravitational slingshot maneuver. They needed to gain experience, to test the technique, while simultaneously ticking off their now most pressing planetary targets, the gas giants, Jupiter and Saturn themselves. And so, in 1969, the agency signed off on a pair of new spacecraft to be developed as part of their existing Pioneer program. This program, which had seen earlier successes with a series of spin-stabilized probes designed to study space weather and the interplanetary environment, had lain dormant for some years. These new missions, however, then designated simply as Pioneer F and Pioneer G, would carry over the successful proven design philosophies of their predecessors, but would incorporate them into a new, more streamlined and significantly more resilient pair of probes. These would be spacecraft fit for a much longer, much more demanding interplanetary voyage, a voyage that would take them, for the first time, into the largely uncharted territory of the outer solar system. The former of these, today known to history as Pioneer 10, was tasked with becoming the first robotic emissary to successfully cross the perilous asteroid belt and reach the giant planet Jupiter. There, it would conduct its scientific investigations before receiving a powerful gravitational boost that would ultimately shoot it off on a trajectory into the even deeper unknown of interstellar space. Pioneer G, on the other hand, later christened Pioneer 11, would meticulously repeat these same initial steps, journeying to Jupiter for its own gravitational slingshot. But unlike its sibling, Pioneer 11 would use its Jovian boost to carry it onwards to the other majestic gas giant, Saturn, thereby becoming the first human-made object to visit the solar system's ringed crown jewel. Hundreds of ambitious scientific experiments were proposed for these intrepid probes, and their complex construction was estimated to have required more than 25 million working hours, a testament to the dedication and ingenuity of the teams involved. Aboard their final carefully selected sets of mounted instruments were helium magnetometers for studying magnetic fields, plasma probes for analyzing charged particles, charged particle detectors, cosmic ray telescopes for observing high-energy radiation from deep space, general radiation detectors, asteroid and meteorite trackers for navigating the hazards of interplanetary space, Geiger tube telescopes for measuring radiation levels, and finally, a suite of sophisticated optical instruments for studying their target worlds in visible, ultraviolet, and infrared wavelengths. The stage was set for humanity's first dedicated exploration of the realm of the giants. Pioneer 10, humanity's first bold emissary destined for the outer solar system, embarked on its historic journey from the launch pads of Cape Canaveral on the 2nd of March, 1972. For approximately 4 months, the resilient little probe made its steady way outwards, traversing the interplanetary void that separates Mars from the inner edge of the vast asteroid belt, that circumstellar fence of rocky projectiles and primordial debris lying primarily between the orbits of Mars and Jupiter. It formally entered this largely uncharted territory on the 15th of July. But unlike the dramatic, asteroid-dodging sequences often depicted in science fiction, Pioneer 10's passage through the belt was remarkably smooth, almost anticlimactic. The asteroid belt, while populous, is also incredibly vast, and the probe barely strayed within 10 million kilometers of any significantly large object during its 7-month transit through its interior. The chances of a direct collision, while not zero, were statistically very low. And save for some negligible, almost imperceptible impacts with tiny dust particles, Pioneer 10 emerged from the far side of the asteroid belt entirely unscathed on the 15th of February in the following year, 1973. Having successfully navigated this first great hurdle, it immediately started to return the first pioneering heliophysics data from the largely unknown space beyond the familiar terrestrial neighborhood. It diligently probed the characteristics of the solar wind at these greater distances, analyzing its speed, density, and chemical constituents. It sniffed out traces of cosmic dust, providing insights into the distribution of matter in the outer solar system, and, remarkably, it detected the first helium atoms believed to originate from the interstellar medium, a faint whisper from the galaxy beyond our sun's influence. After successfully clearing the asteroid belt, Pioneer 10 maintained its determined outwardly passage for a further 9 months, steadily closing the immense distance to its primary target. Eventually, it came within 25 million kilometers of the colossal gravitational presence of Jupiter, and on the 6th of November, 1973, it officially initiated its observations phase. In the month that followed this milestone, the probe drew ever closer to the Godfather planet, its instruments keenly studying Jupiter's turbulent atmosphere and its complex surrounding environment of radiation belts and moons. In doing so, It amassed the first significant collection of more than 500 groundbreaking images of the gas giant, providing humanity with its first relatively close-up views of its swirling, banded cloud tops and its iconic, centuries-old storm, the Great Red Spot. The probe made its closest approach to Jupiter on the 3rd of December, 1973, a moment of triumph and trepidation for its controllers back on Earth. But as the brave little craft crossed Jupiter's powerful magnetic equator, it was suddenly and violently exposed to a huge, unexpected flux of high-energy electrons, a barrage of radiation some 10,000 times stronger than the most corrosive radiation belts found around Earth. This intense bombardment wreaked havoc on the probe's sensitive electronic instruments, generating a cascade of erroneous commands that threatened to derail the entire mission at its most critical juncture, while its dedicated engineers on Earth, working tirelessly across vast distances, were able to remotely diagnose and rectify most of the troubling issues, scrambling to send corrective commands. Only 6 of the spacecraft's 11 core scientific instruments remained fully operational as they were subsequently turned back to image Jupiter's fascinating family of large moons. As a direct result of this radiation damage and the ensuing command glitches, a planned image of the volcanically active moon Io, as well as some valuable close-up shots of Jupiter itself, were unfortunately lost. And while the craft was able to capture images of 2 of the other large Galilean moons, Europa and Ganymede, only the images of the giant moon Ganymede yielded scientifically meaningful detail from this pioneering encounter. Upon successfully navigating these challenges and starting its exit from the Jovian system on the 4th of December, Pioneer 10 etched its name into the annals of space exploration yet again. It became the very first probe to receive a significant gravitational assist from another planet, a precisely calculated slingshot that catapulted the craft with newfound velocity en route towards its ultimate, poignant destination, the cold, dark, and largely unknown expanse of interstellar space. Having accrued so much additional velocity from its carefully choreographed trajectory through the Jupiter system, Pioneer 10 had now been set on an irreversible path, becoming the first man-made object ever to reach the solar system's escape velocity, that critical speed needed to overcome the relentless gravitational pull of the Sun for the duration of its long journey beyond the planetary realm. Covering more than 500 million kilometers every year, a testament to Jupiter's gravitational gift, Pioneer 10 crossed the distant orbit of Saturn just 3 years later, in 1976. This was followed by its passage beyond the orbit of Uranus in 1979, and then its crossing of Neptune's far-flung orbital path in 1983. It would continue along this solitary, though ever outward path for another 15 years almost, its system slowly degrading, its power source gradually waning, before its vanishingly weak radio signal finally became too faint, too attenuated by the immense distance, to transmit any reliably readable data back to its anxious listeners on Earth. But while the mission was officially declared, concluded on the 31st of March, 1997, the resilient Pioneer 10, a true pioneer in every sense, would continue to beam back the occasional featureless telemetry signal like a faint, dying heartbeat for a further 6 remarkable years. In fact, the very last confirmed contact with this trailblazing probe was made on the 23rd of January, 2003, from an astonishing distance of more than 80 astronomical units, 80 times the distance between the Earth and the Sun. This final, faint whisper finally capped off what was originally intended to be a daring, but relatively short, 21-month mission. Instead, it had endured for more than 30 incredible years, a true, enduring testament to the brilliant engineering of the craft, the foresight of its designers, and the considerable time and effort that was invested in future-proofing its design for a journey into the unknown. Just over a year after the triumphant launch of Pioneer 10, its designated follow-up mission, then known simply as Pioneer G, but soon to be christened Pioneer 11, was meticulously prepared to follow in its siblings' groundbreaking wake. Like the former, this spacecraft was designed to float serenely across the vast expanse of the asteroid belt, navigating its scattered hazards on its long route towards the immense Jovian system. There, it too would pass by the colossal gas giant, Jupiter, to receive a carefully calculated gravitational boost. But unlike its predecessor, which was unceremoniously slingshotted straight out into the depths of deep space after its Jovian encounter, Pioneer 11 had a different, additional objective. It would skillfully use its Jovian gravitational assist to carry it onwards towards the other magnificent gas giant of our solar system, thereby becoming the very first robotic probe to visit the solar system's undisputed crown jewel, the ringed wonder that is Saturn. Once there, its mission was to diligently study Saturn's atmosphere, its complex magnetosphere, its iconic, unparalleled planetary rings, and the many intriguing, diverse moons that dance in orbit around this majestic giant. And upon the successful completion of those pre-programmed objectives at Saturn, Pioneer 11 was also tasked with a daring secondary experiment. It would be used to test a slingshot maneuver of its own, one that involved flying precariously through Saturn's expansive ring plane. The probe lifted off from the familiar launch pads of Cape Canaveral on the 5th of April, 1973, embarking on a slightly longer 18-month voyage to Jupiter, a journey that also included its careful transit through the asteroid belt. It encountered the giant planet in November of 1974 and made its closest approach a month later. On the 2nd of December, it came within just 43,000 kilometers of Jupiter's swirling cloud tops, a daring pass nearly 3 times closer than its counterpart, Pioneer 10 had managed the year before. However, it executed this closer approach at a much higher velocity, resulting in a significantly less prolonged exposure to the planet's damaging radiation belts. As such, a crucial difference emerged. All of the craft's 11 scientific instruments this time survived their close encounter with Jupiter fully intact and operational. This allowed Pioneer 11 to snap over 200 even sharper, more detailed images of the planet, including the very first revealing shots of its enigmatic polar regions and more breathtaking vistas of its swirly, banded outer atmosphere. The probe also enjoyed considerably more success in studying Jupiter's Galilean moons, capturing valuable images of the volcanic moon Io and the cratered moon Callisto, where Pioneer 10 had unfortunately been unable to, due to its radiation-induced instrument malfunctions, upon receiving its bespoke gravitational boost from Jupiter, precisely tailored for its onward journey. Pioneer 11 would then venture outwards through the cold and dark of interplanetary space for another 5 long years before it finally encountered its next eagerly awaited target, the majestic, ringed planet Saturn. On the 29th of August, 1979, Pioneer 11 officially entered the Saturn system and spent the next 3 days steadily sinking towards the planet, on a trajectory that would take it to its closest approach, a mere 21,000 kilometers from Saturn's visible outer edge. All the while, its cameras were diligently snapping increasingly close-up images of the ringed giant and its spectacular accoutrements. It then achieved another historic first. It became the first probe to successfully cross Saturn's expansive ring plane. This was not merely a scientific curiosity, it was a crucial dry run, a pathfinder mission for the more sophisticated Voyager spacecraft, which were, by this time, already well on their way to the gas giant, following in Pioneer's wake. In order to receive the kind of powerful gravitational boost from Saturn that would be required to push the Voyager probes further out into the solar system towards Uranus and Neptune, it is necessary for a spacecraft to fly relatively close to the planet. This, in turn, means that the extended ring plane, composed of countless particles of ice and dust, must be breached. Therefore, Pioneer 11 was tasked with bravely practicing flying through a known gap in the rings, specifically the gap between the A ring and the F ring, in order to map out a sufficiently clear and safe route for the upcoming Voyager encounters. The stakes were high. If Pioneer 11 had sustained any serious damage from colliding with unseen moonlets or larger ring particles during this daring passage, the ambitious Voyager, 2 ice giant, mission to Uranus and Neptune would probably have been deemed too risky and subsequently scrapped. But the resilient Pioneer 11 glided through the ring plane smoothly, encountering no significant problems, its instruments detecting only a few minor impacts from tiny particles. It successfully received its gravitational assist from Saturn, a final cosmic push that sent it hurtling onwards, embarking on the interstellar phase of its own remarkable mission, destined, like its sibling, to eventually leave our solar system behind. The Pioneer probes, both 10 and 11, maintain their silent, outward passages to this very day, both now well over 100 astronomical units from Earth, verging on the very periphery of the Sun's extended atmosphere, the heliosphere, and approaching the boundary with true interstellar space. And their lonely journeys will continue for uncounted millions of years to come. First, formally entering the vast emptiness between the stars, and then, in the unimaginably distant future, eventually passing by other distant stars in the constellations of Taurus and Scutum, silent, fleeting testaments to a species that dared to reach out from its small blue world. One can only guess, with a sense of profound wonder and perhaps a touch of hopeful trepidation, at what or who these intrepid pioneer probes might eventually encounter given enough time, enough eons drifting through the cosmic dark. Perhaps, in some far-flung future, the pioneers will silently pass by planets orbiting other stars, worlds that might, just might, host intelligent life, civilizations capable of recognizing these tiny, ancient emissaries from a long-dead star system. And though both probes are now entirely defunct, their power sources faded to nothing, their instruments cold and silent, their creators did make alternative, rather optimistic arrangements for just such an improbable eventuality. Attached securely to the antenna support struts of both spacecraft, shielded from the worst of micrometeoroid erosion, is a unique postcard from humanity, a message in a bottle cast into the cosmic ocean, intended for anything or anyone that might stumble upon them in the distant, unknowable future. These are the Pioneer Plaques. Designed by a team led by the visionary astronomer Carl Sagan and his peers, the Pioneer Plaques are distinctive, gold-finished, anodized aluminum slabs, meticulously inscribed with a wealth of general information about humanity and our place in the cosmos. Each plaque includes a schematic depiction of a human male and female body, overlaid on an outline of the Pioneer probe itself to provide a sense of scale. It also depicts the relative positions and sizes of the planets in our solar system, indicating Earth as the point of origin. Perhaps most ingeniously, it features a pulsar map, a kind of cosmic address, designed to allow any sufficiently advanced civilization to triangulate the position of our home planet, using the precisely timed emissions from 14 known pulsars, rapidly spinning neutron stars, as celestial reference points. However, it must be acknowledged that each one of these carefully chosen symbols has since been criticized by some for being much too anthropocentric, reflecting a human-centric view of the universe, not to mention the practical fact that the pulsar map, based on the observed rotational periods of those neutron stars at the time of launch in the early 1970s, is now, due to the gradual spin-down of pulsars over time, largely obsolete as a precise navigational tool. But if nothing else, these plaques and their accompanying probes are unmistakably, undeniably engineered artifacts. They bear the clear stamp of intelligence, of deliberate design. And if intelligent life does indeed exist around other stars, as Sagan so fervently predicted and hoped, then perhaps, one day, in a future almost too distant to imagine, they may see these ancient probes streaking silently across their skies, a curious anomaly from a forgotten corner of the galaxy. Imagine, for a moment, if we, here on Earth, found something like this, an alien probe coursing through our own solar system. The repercussions on our society, our culture, our science, and our politics would be utterly unprecedented, profoundly transformative. With both of the solar system's gas giants successfully reached and briefly surveyed by the pioneering flyby missions of the 1970s, the clear next step in their exploration, by the dawn of the 1980s, would be to return to these majestic worlds with more persistent, more capable probes. These would be spacecraft capable of not just flying past in a fleeting encounter, but of actually entering into orbit around Jupiter and Saturn, allowing for long-term, detailed study. In the decade just gone, dedicated Mars orbiter probes had transitioned dramatically from the realm of science fiction to established reality, most notably through the groundbreakingly successful Mariner 9 mission, which meticulously studied the red planet from orbit for more than 8 months throughout 1972. Therefore, when serious work began on a dedicated Jupiter orbiter later that same decade, it was natural that successful design philosophies and engineering lessons learned from the Mariner program would be carried over and adapted for this new, more ambitious endeavor. But by the time this Jupiter-bound probe finally materialized, almost a full decade later, its technology and capabilities had evolved so significantly beyond its Mariner-based origins that its administrators felt it warranted its own distinct mission classification, and thus it was proudly reassigned as the Galileo spacecraft, named in profound honor of the great 17th century Italian astronomer who first turned his telescope to the heavens and discovered the 4 large Jovian moons that now bear his name, Galileo Galilei. This sophisticated new probe consisted of 2 primary components: a main orbiter, designed for long-term study of the entire Jovian system, and a smaller, detachable atmospheric entry module that would be bravely dropped directly into Jupiter's turbulent upper atmosphere to sample its conditions firsthand. However, the cutting-edge technology required to both develop and rigorously test this innovative Galileo entry probe would not become fully available until well into the 1980s, and a host of other unforeseen factors also conspired to hamper and significantly delay the Galileo mission. Everything from persistently bad weather at launch sites, critical test failures during development, and even lawsuits targeting the probe's onboard nuclear power source contributed to pushing its launch date back repeatedly. The tragic Challenger disaster in 1986 also had a profound impact, grounding the space shuttle fleet for an extended period and forcing a complete re-evaluation of launch strategies for interplanetary missions. As a result of this cascade of setbacks, Galileo's launch was delayed all the way through until 1989. But at long last, the much-anticipated probe did finally lift off from Earth on the 18th of October, 1989, nestled securely in the cargo bay of the space shuttle Atlantis, which delivered it safely to a low Earth orbit. From there, it would then execute a precisely choreographed series of engine burns and delicate thruster firings to guide it into a heliocentric, or sun-centered, orbit. This carefully planned trajectory was designed to allow it to receive crucial gravitational slingshots and necessary course corrections from close flybys of both Venus and Earth itself, building up the momentum required for its long journey outwards. After accruing enough velocity from these planetary encounters, the probe then embarked on a long, gracefully arcing trajectory that took it once again through the asteroid belt, before finally coming within range of the mighty Jupiter system in mid-July of 1995, nearly 6 years after its launch. Almost immediately upon its arrival in Jupiter's sphere of influence, the Galileo entry probe was released from the main orbiter and began its slow, deliberate drift towards the swirling cloud tops of the giant planet, its parent orbiter faithfully accompanying it on a parallel course. It would take another 5 anxious months before the entry probe finally breached Jupiter's upper atmosphere on the 7th of December, 1995, hitting the outer layers at a blistering speed of around 50 kilometers per second. It then spent approximately 1 hour courageously sinking beneath the cloud's edge, plunging to a depth of more than 180 kilometers. This was hardly scratching the surface in the grand scheme of Jupiter's immense internal structure, which extends tens of thousands of kilometers deeper, but it still returned invaluable first-hand insights on the increasingly hellish conditions unfolding below. It measured chaotic, super hurricane wind speeds of almost 2,000 kilometers per hour, with ambient temperatures climbing rapidly to a scorching 16,000 Kelvin, before the probe's ablative heat shield finally, inevitably, succumbed to the ferocious heat and pressure, and its radio signal fell silent. Back in the relative safety of space, the main Galileo orbiter prepared to fire its own engines, executing a critical deceleration burn to allow it to be captured by Jupiter's immense gravity and achieve a stable orbit. This maneuver was successfully completed on the 8th of December, 1995, making Galileo the first robotic probe ever to be captured into orbit around a world in the outer solar system, a truly historic achievement. Over the next 7 years and 9 months, a remarkably long operational life, it would make no less than 35 long elliptical laps around the complex Jupiter system. Its orbit was cleverly designed so that it spent only relatively short periods of time up close with the giant planet itself, thus allowing its sensitive instruments crucial time to recover from the intense exposure to Jupiter's powerful radiation belts. Over the course of its extended mission, Galileo assembled an extensive, comprehensive, and often astonishing dataset for the Godfather planet and its diverse surrounding environment, making a string of astounding discoveries on both counts. It captured dramatic images of an active volcanic eruption on the tortured, tidally heated moon of Io, and upon closer inspection of its surface, revealed vast, flowing lava fields for the very first time, confirming Io as the most volcanically active world in the solar system. It also mapped the surface of the giant moon Ganymede, the largest moon in our solar system, in much greater detail than ever before, identifying complex tectonic features and, most surprisingly, discovering that Ganymede possesses its own intrinsic magnetic field, a rarity for moons, leading to complex magnetic interactions with Jupiter's own magnetosphere. And perhaps most tantalizingly so, on the icy moon Europa, Galileo uncovered the strongest, most compelling evidence yet for a long speculated vast ocean of liquid salt water hidden beneath its smooth, frozen crust. An ocean atop which the moon's icy shell is thought to be suspended and decoupled, potentially warmed by tidal forces. This discovery immediately propelled Europa to the forefront of the search for habitable environments beyond Earth. Upon finally exhausting its precious maneuvering fuel reserves in September of 2003, the Galileo spacecraft's engines were fired for the very last time, in a poignant final act. The probe was intentionally and precisely steered on a collision course with Jupiter itself. This was a carefully considered decision, made to ensure that the now uncontrolled spacecraft would not inadvertently crash on one of Jupiter's potentially life-bearing moons, particularly Europa, and contaminate a pristine, potential subsurface ocean with earthly microbes. It dutifully followed its long-lost entry probe to a crushing demise within Jupiter's immense atmosphere, and triumphantly, if silently, concluded its groundbreaking mission on the 21st night of September 2003. But as one door of discovery slammed shut with Galileo's fiery end, another was just beginning to swing open. For the end of the Galileo mission to Jupiter almost perfectly coincided with the eagerly anticipated start of the first dedicated Saturn orbiting mission by the magnificent international spacecraft known as Cassini-Huygens. The torch of outer planet exploration was about to be passed. The Cassini-Huygens spacecraft stands as one of the undisputed flagship missions of the 21st century, a monumental collaborative effort that redefined our understanding of the Saturnian system, like Galileo before it. The spacecraft consisted of two main components, a large, sophisticated orbiter named Cassini, designed for years of detailed study, and a smaller, detachable probe named Huygens. But this time, the probe was not designed for atmospheric entry into the gas giant itself. Rather, Huygens was a dedicated landing module built for the audacious task of plunging into the thick, dense, hydrocarbon-rich clouds that completely shroud the surface of Titan, Saturn's largest and most enigmatic moon. This ambitious mission was first conceived in the early 1980s, only a short time after the tantalizing flyby success of Pioneer 11 had given humanity its first close-up glimpse of Saturn. Recognizing the immense scientific potential of a long-term Saturn orbiter, the United States National Academy of Sciences formed a powerful coalition with European scientific partners, eyeing future collaborative missions that could pool resources and expertise. A dedicated Saturn orbiter, with a specific focus on studying both the gas giant itself and its principal planet-like moon Titan, quickly emerged as the general consensus for a high-priority mission. However, its early development was unfortunately stunted by persistent financial disagreements and political squabbles, particularly on the American side of the partnership. Eventually, however, after years of negotiation and refinement, NASA, the European Space Agency, and the Italian Space Agency all firmly committed to the ambitious project. The mission was officially designated Cassini-Huygens, a fitting tribute to two prominent 17th-century European astronomers who made seminal, foundational contributions to the early study of the ringed gas giant. Giovanni Cassini, an Italian astronomer, meticulously studied Saturn and its surroundings, and was the first to identify the distinct gaps within its magnificent ring structure, including the prominent division that now bears his name. Christian Huygens, a Dutch astronomer and physicist, meanwhile, was the first to correctly conclude that these mysterious, luminous rings were not actually part of Saturn itself, but were instead a separate, orbiting disk of material. He also holds the distinction of spotting Saturn's largest moon, Titan, way back in 1655. And just like its illustrious namesake astronomers, the Cassini-Huygens spacecraft was designed to perform extensive, detailed analyses of Saturn, its complex ring system, and its diverse family of moons, targeting more than 20 distinct objects during the primary phase of its meticulously planned mission. During this time, it would undertake the critical task of releasing its precious landing module, the Huygens probe, which would then bravely descend through Titan's opaque atmosphere to land upon its mysterious, frozen surface, giving humanity our very first, long-awaited look under the hood at this fascinating, complex atmospheric oddity, a world often described as a primordial Earth in deep freeze. After around a decade in careful development and rigorous testing, the massive Cassini-Huygens spacecraft, a marvel of engineering weighing nearly 6 metric tons, lifted off from Cape Canaveral on the 15th of October, 1997, commencing its 7-year interplanetary voyage towards the solar system's distant crown jewel. After entering its initial heliocentric orbit, the craft skillfully gathered pace and energy with 2 precisely timed flybys of Venus in the 2 years that followed. This gravitational ballet gave it the necessary kick, the velocity boost it required to embark on its long, arcing voyage out to Saturn. Along the way, it also called at Jupiter in December of the year 2000 for an additional powerful gravitational assist. And despite only spending a relatively short while in the Jovian system during this flyby, Cassini's advanced instruments snapped over 26,000 stunning, high-resolution images, among them some of the most iconic and breathtaking shots ever taken of the Galilean moons dramatically eclipsing the swirling cloud decks of their immense host planet. During its transit between Jupiter and Saturn, the spacecraft also took the opportunity to beam powerful radio signals directly at the Sun and then detect them as they passed close to its limb, a clever experiment designed to precisely test the predicted curvature of space-time, and thus the accuracy of Einstein's general theory of relativity under the influence of the Sun's immense gravity. It then finally started its intricate approach sequence towards Saturn in June of 2004, preparing to execute the first in a series of complex, inherently risky orbital insertion maneuvers. In order to achieve a stable orbit around Saturn, the craft had to perform a daring roll back on itself maneuver, turning to fire its main engines along its path of travel to significantly decelerate, slowing down just enough so that it could be gently captured into orbit by Saturn's powerful gravitational pull. This critical burn required briefly misaligning Cassini's high-gain antenna with the Earth, meaning that for a tense period, its controllers on Earth were effectively flying blind, unable to receive telemetry or send commands. But the robust spacecraft came through the challenging maneuver flawlessly nonetheless, and triumphantly reconnected its communication link with the Deep Space Network to officially commence with its ambitious 4-year primary mission of exploration in the Saturn system. First up on its busy agenda were a series of carefully targeted flybys of a number of Saturn's smaller, enigmatic, icy moons. It passed by the dark, cratered moon Phoebe on the 11th of June, studying its unusually bright patches to infer the presence of significant quantities of water ice on its surface, suggesting it might be a captured object from the outer solar system. Soon after, through careful analysis of early Cassini images of the system, 3 previously unknown tiny moons, today known as Methone, Pallene, and Polydeuces, were identified lurking within Saturn's rings and nearby orbits. But the spacecraft was soon focused with intense scrutiny on its principal satellite target, the mysterious, veiled Moon Titan, that unique, planet-like world with a thick, nitrogen-rich atmosphere, quite unlike anything else found in our entire solar system. As such, Titan has always been viewed as an absolutely essential component of any comprehensive mission exploring the Saturnian system, and Cassini was no exception, carrying out no less than 45 close flybys of this fascinating moon during its initial 4 years of operation alone. The very first of these close encounters came in October of 2004, when it passed about 1,200 kilometers from the hazy tip of Titan's extensive clouds. Its powerful infrared and ultraviolet instruments then began the painstaking process of peeling back the layers of this opaque atmosphere for the very first time, slowly compiling preliminaries radar-generated maps of Titan's hidden surface features, with a keen view to identifying a safe and scientifically interesting landing site for the patiently waiting Huygens probe. And then, on Christmas Day, 2004, in a poignant moment of interplanetary gift-giving, Cassini's precious cargo, the Huygens probe, was gently released, sent hurtling down on its one-way journey towards Titan's obscuring clouds. It finally penetrated their hazy outer edge around 3 weeks later, beginning its perilous descent. It diligently recorded and relayed data throughout its entire 2.5-hour atmospheric entry and parachute-assisted descent, beaming back around 350 remarkable pictures of its approach, though, frustratingly, a further 350 images were tragically lost due to an uncorrected software configuration error between the probe and the orbiter, But on the 14th of January, 2005, a date now etched in the history of planetary exploration, the Huygens probe successfully touched down in Titan's equatorial Adiri region, a vast, dark, dune-filled plain. Miraculously, it continued to broadcast what it saw and sensed from the alien surface for a further 90 precious minutes, far exceeding its design expectations. In that brief window of time, it captured and transmitted the very first, and still the only, panoramic glimpse we have ever obtained from the surface of a solid body in the entire outer solar system. These extraordinary images show a landscape strewn with rounded boulders, not of rock, but of highly reflective water ice, frozen as hard as granite by Titan's brutal ambient surface temperature of minus 180 degrees Celsius. But what makes this alien vista particularly intriguing is that these icy boulders appear to have been significantly smoothed and eroded by the flow of some other liquid, though certainly not water at this incredibly low temperature. Rather, as Cassini's subsequent radar observations would indisputably confirm in 2006, Titan is home to a vast, planet-wide network of lakes, rivers, and even seas, not of water, but of liquid methane and ethane, hydrocarbons that exist as liquids at Titan's frigid temperatures. In fact, Titan possesses a complex methane cycle which bears striking, almost eerie similarities to the familiar water cycle here on Earth, complete with clouds, rain, rivers, lakes, and evaporation. And if we were to somehow warm Titan up in the very distant future, perhaps when our sun swells into a red giant, this liquid methane would evaporate completely, and the vast mountain ranges made of water ice would finally melt, potentially taking its place. Thus, in the unimaginably remote future, long after Earth has been rendered uninhabitable or even swallowed whole by our dying sun, it is perhaps Titan, with its abundant surface-dwelling organic compounds and the potential for liquid water, that may hold the best hope for a future awakening of life in our solar system. Another of Saturn's diverse moons with intriguing, if different, prospects for habitability is the small, icy world of Enceladus. Though it bears a quite different set of potentially life-giving characteristics compared to Titan. Enceladus is much smaller than Titan, and it lacks a substantial, protective atmosphere capable of supporting life on its deeply frozen, globally cracked surface. But much like Jupiter's enigmatic moon, Europa, Enceladus is now strongly thought to possess a vast, buried, subsurface oceanic layer of liquid salt water, an ocean which is kept warm and liquid not by sunlight, but by intense tidal heating, generated by gravitational resonances and interactions within the complex Saturn system. These relentless gravitational tugs and pulls cause friction deep within the moon's rocky interior, resulting in energetic, hydrothermal upwellings in its hidden liquid layer. These upwellings then press against the overlying icy surface and sometimes refreeze, creating the characteristic faults, ridges, and tiger stripes observed on its surface, and sometimes even causing spectacular cryovolcanic eruptions, geysers of water ice and vapor spewing into space. In 2005, just about 2 months after the Huygens probe had successfully touched down on Titan, Cassini's keen instruments saw the distinct outline of a massive ice geyser eruption occurring at Enceladus's south pole as it spurted out vast plumes of material, which regularly fall into orbit around Saturn, forming and replenishing the diffuse E-ring with fresh, frozen material. A few years later, Cassini went one better, achieving an even more remarkable feat. It flew straight through one of these water-rich plumes during a daringly close flyby of Enceladus, directly sampling its chemical constituents. This audacious maneuver all but confirmed the presence of a tidally heated, salty liquid ocean beneath its icy shell, an ocean potentially containing organic molecules and the necessary ingredients for life. With so much exciting scientific potential seemingly locked away within these fascinating moons, Titan and Enceladus, it's sometimes easy to lose sight of Cassini's other extensive and equally important studies, including its incredibly detailed analyses of Saturn's magnificent rings. Using a variety of techniques, including radio signals and stellar occultation, Cassini's instruments meticulously determined the three-dimensional structure, the complex dynamics, and the particle size consistency of their countless constituent moonlets and icy grains. It identified both incredibly fine, intricate structures within the rings, revealing waves, spokes, and braids, as well as more complex, gravitationally bound clumps of material, small moonlets, actively clearing distinct gaps and carving sharp edges in the ring's otherwise uniform material. The probe also dedicated significant time to studying a number of extreme and bizarre weather events playing out in Saturn's deep upper atmosphere. This began in 2006, when a powerful, Earth-sized cyclone, complete with a distinct eye wall, was seen churning near one of its poles. It also conducted long-term observations of one of the planet's most jaw-dropping and enigmatic features, its iconic North Pole hexagon. This is another enormous, six-sided, eyed storm system, extending almost 30,000 kilometers across, which was originally discovered by the Voyager spacecraft in the early 1980s. Between 2008 and 2017, Cassini meticulously observed gradual, subtle color changes occurring within this astonishing cloud pattern, likely in response to seasonal changes in its exposure to sunlight as Saturn progressed through its nearly 30-year orbit around the Sun. And then, in 2010, it witnessed something truly spectacular, a phenomenon visible from Earth only once every 30 Earth years or so, the eruption of Saturn's Great White Spot. This colossal storm bears some resemblance in scale to Jupiter's famous Great Red Spot, but unlike the latter, it did not persist for very long in one location or maintain a stable structure. Instead, it erupted violently, then whipped rapidly around the face of the planet, leaving long, distinctive trails of suspect white discharge, likely ammonia ice crystals, in its turbulent wake, which slowly faded away over a number of subsequent years. By this time, around mid-2008, Cassini had successfully completed the primary phase of its ambitious mission, which had lasted for 4 incredibly productive years, but with plenty more maneuvering fuel still left in its tanks, and its robust radioisotope thermoelectric generator power source still well conserved and producing ample electricity. Its dedicated engineers on Earth were able to confidently extend Cassini's operational life by an additional 2 years. This extension enabled the probe to meticulously study Saturn during its equinox event in 2009, a period when the sun illuminates the ring's edge on, providing unique scientific insights, thus coining the mission extension's official title, the Cassini Equinox Mission. And upon the successful conclusion of this equinox phase, in June of 2010, Cassini's mission was, remarkably, renewed yet again. This time, for another substantial 6.5 years, a period designated the Cassini Solstice Mission. This would take its operational life all the way through to observe Saturn's northern summer solstice in 2017. This extraordinarily long extension allowed for another 155 full revolutions of Saturn, 54 more close flybys of the enigmatic moon Titan, and 11 more daring passes by the cryovolcanically active moon Enceladus, vastly expanding its already rich data set. But by the time these extended objectives were completed, the stalwart craft really was starting to run on fumes, its propellant reserves dwindling to critical levels. And thus, as its ultimate poignant act, Cassini's ingenious engineers directed it to execute its so-called grand finale routine. This was the very last, carefully choreographed part of the mission, one which would entail the riskiest, most daring maneuvers attempted yet. In April of 2017, Cassini's orbit was precisely adjusted to guide it through a previously unexplored gateway in Saturn's rings. Passing a breathtakingly close 300 kilometers from the visible inner edge of the D-ring, it then made a further 22 nail-biting orbits through this narrow gap between the innermost rings and Saturn's upper atmosphere, enabling it to attain the closest, most detailed observations yet of Saturn's atmosphere, its dynamic weather patterns, and the intricate structure of its rings from an entirely new perspective. It took its final haunting images of the giant planet and its majestic system in September of that year, before being intentionally, and with a sense of profound respect, flown into Saturn's atmosphere. This, once again, was a deliberate act of planetary protection, a final sacrifice to avoid any remote possibility of the now uncontrolled spacecraft accidentally contaminating a potentially life-bearing moon like Titan or Enceladus with earthly microbes. And there is a popular, widely circulated image, a truly breathtaking shot purporting to be Cassini's final, dramatic glimpse of Saturn, just moments before it plunged to its crushing demise. But alas, this evocative image is just a talented artist's impression, often mistakenly passed off as the truth on social media. In reality, Cassini's very last, scientifically valuable view of Saturn was actually a much less visually interesting, though still data-rich, image. It then finally, silently, dropped into the gas giant's upper clouds on the 15th of September, 2017, bringing to a dignified close more than a decade of revolutionary discoveries and an unparalleled bounty of stunning, awe-inspiring shots of the entire Saturn system. The data it returned will keep scientists busy for decades to come, and it may be many more decades before we see another dedicated Saturn orbiter that reveals as much or touches our collective imagination as deeply as the magnificent Cassini spacecraft did. The question that naturally arises then is what is actually on the drawing board. What missions are actively being planned for the near future to continue this grand exploration of the gas giants and their captivating moons? Well, in more recent years, missions targeting the gas giants have become increasingly, and understandably, more aligned with the intensive study of their diverse families of moons, with a particularly sharp, central focus on assessing the potential for habitability around Jupiter's ocean moon, Europa, and Saturn's methane-rich world, Titan, as the closer of the two giant planets. Jupiter and its system have enjoyed somewhat more sustained attention from scientists in the years since the conclusions of the Galileo and Cassini orbital missions. In that time, we've successfully re-established a persistent, dedicated robotic presence around Jupiter with the Juno spacecraft, the second impressive installment of NASA's ambitious New Frontiers program. Juno is, in many ways, the culmination of a number of restructured and rescoped projects that were targeting Jupiter, and specifically Europa, in the 2000s, before finally getting off the ground and launching successfully in August of 2011. Among its primary scientific aims was to gain much deeper insight into Jupiter's complex internal structure, helping to shore up our evolving theories on its formation within the early solar nebula and its subsequent evolution over billions of years. And Juno continues its diligent study of the godfather planet's dynamic weather systems, its powerful, sprawling magnetosphere, and the precise chemical composition of its deep atmosphere to this very day, with its current mission extension taking its operational life through to at least 2025, continuing to return a stream of valuable data and breathtaking images. And as the 2030s approach, a new generation of sophisticated Jupiter system probes are slated to take to the skies, ready to take Juno's place and build upon its legacy. The first of these, belonging to the European Space Agency, is the Jupiter Icy Moons Explorer Probe, or JUICE, which successfully launched earlier this year, in April of 2023. As of the making of this video, the JUICE probe is currently trailing the Earth in a carefully planned heliocentric orbit, due to make crucial gravity-assist flybys of both our world and Venus in the coming years, as it gradually gathers the necessary pace and energy for its long trip out through the asteroid belt. It won't actually arrive at its destination in the Jovian system until 2031, a testament to the long journey times involved even with clever orbital mechanics. But when it does arrive, its primary mission will be to conduct detailed studies of the large Galilean moons Ganymede, Callisto, and Europa, making new, high-resolution maps of their diverse surfaces, while also actively searching for further signs of subsurface oceans and the presence of complex organic compounds, key ingredients for life. And shortly after JUICE's arrival, it is expected to be joined in orbit around Jupiter by NASA's own dedicated Galilean moon explorer, the Europa Clipper mission. This spacecraft, as its name suggests, will also maneuver extensively around the Jovian system, performing dozens of detailed reconnaissance flybys of the potentially habitable moon Europa, while also specifically searching for an active plume of erupted seawater to bravely fly through, much like Cassini did so successfully at Enceladus, in order to directly sample its composition. The Europa Clipper mission is currently set for launch in October of 2024, though due to its more direct and powerful trajectory, it won't take as long to reach Jupiter as the JUICE probe, and so will probably begin its primary science mission at a similar time in the early 2030s, leading to an exciting period of tandem exploration. Plans for a dedicated landing module extension for Europa Clipper, similar in concept to the Huygens probe, for dropping down onto Europa's icy surface to search for biosignatures, have also been tabled and extensively studied, nicknamed the Europa Lander. But this ambitious proposal, unfortunately, did not make it into NASA's finalized, funded plan for the Clipper mission, and is thus unlikely to materialize any time in the next decade, remaining a tantalizing prospect for the future. But something we may get a much better, more detailed glimpse of by then is Saturn's largest moon, Titan, while the resounding, comprehensive success of the Cassini-Huygens mission has understandably resulted in dedicated Saturn system probes taking more of a back seat in current mission planning. There is still a firm date penciled in for 2027, which will see the launch of a truly innovative probe designed to implement the successful, revolutionary designs from NASA's Mars Ingenuity helicopter, but this time on the surface of Titan. This exciting mission is called Titan Dragonfly. It is planned to land in Titan's equatorial Shangri-La dune fields sometime late in the next decade, and from there, this nuclear-powered quadcopter will take dozens of controlled atmospheric flights, hopping from location to location, spanning a total planned traverse of some 175 kilometers, more than double the total distance covered by its pioneering Martian counterpart. This mission will be the fourth exciting installment of NASA's New Frontiers program, the designated successor to the Juno mission which currently circles Jupiter. They are both part of a highly successful program for developing medium-cost, high scientific reward missions, carefully selected by NASA through competitive proposals, for ticking off the remaining high-priority targets for exploration within our solar system, and the very first installment of that groundbreaking New Frontiers program, the New Horizons mission to Pluto and the Kuiper Belt, is one of the few glaring, significant omissions we've yet to cover in this current series on probes that explored the solar system. That, along with the equally revolutionary system-spanning voyages of the twin Voyager spacecraft, and so, it seems we have surely saved some of the very best, most epic tales of exploration for last. Because next time, in the final concluding chapter of this trilogy, we will follow those intrepid spacecraft out on their longest, most audacious ride yet, beyond the familiar edge of the solar system, past the heliopause, and into the true, uncharted depths of interstellar space. Our journey through the realm of the gas giants has revealed worlds of unimaginable scale, of turbulent beauty, and of tantalizing possibility. From the pioneering flybys of the Pioneer spacecraft, which first dared to breach the asteroid belt and brave Jupiter's radiation, to the long-term orbital vigil of Galileo and the breathtaking revelations of Cassini-Huygens at Saturn and its moons. Each mission has peeled back another layer of mystery, painting an ever-richer portrait of our outer solar system. We've seen atmospheres that churn with centuries-old storms, rings that shimmer with icy elegance, and moons that hide secret oceans or mimic a primordial Earth. These robotic emissaries, extensions of our own senses and curiosity, have not only expanded our scientific understanding, but have also touched something deeper within us, a sense of wonder at the diversity of worlds, a connection to the vastness that surrounds our own fragile planet. The challenges were immense, the tyranny of distance, the harshness of the environment, the sheer complexity of the task, yet human ingenuity, perseverance, and an unyielding desire to explore prevailed. And the story is far from over, with Juno currently orbiting Jupiter, and with JUICE, Europa Clipper, and Titan Dragonfly poised to launch in the coming years. A new generation of explorers is preparing to build upon this legacy, to ask new questions, and to seek answers that may one day tell us if we are truly alone in this vast cosmic ocean. The gas giants and their retinues of moons will continue to call to us, their secrets still beckoning from across the void. And as long as we retain that spark of curiosity, that innate human need to reach out and understand, we will continue to answer. The journey continues, always outwards, always seeking,